Yeah. But no, that's not what I mean, it's just like, we don't have. I'm living window. We said I'm living window.
That'd be nice to hang out. Yeah.
Few more minutes here. Just keep-
Sam, then we left shit.
I'm waiting for the time. Yeah.
Different channels, so we'll give them. Like overload. No, I get it. My head turns through so much information, my head turns to mush. But I can still function, I don't know how, but then I'll be, you have to order something from somebody else. I'd rather not. Oh, I just saw that. We don't drink water.
Not there. Yeah, it's already set up. Okay.
Okay. Yeah.
We're both.
Invisible.
I don't think. We don't start with yeah, because she wanted to be somewhere. She couldn't. She could. But she was.
Secure example, I just
Came out of like
consumer key.
her taller ego, just like. And then I just decided like.
Yeah. No, the name is secure exam process. Yeah. You have a.
I was good, but then like.
But then for that, I was like, I don't
That would work, but it's, yeah, it's not far. I live in the neighborhood, it's in St. So, yeah. Like a 15-minute drive. I'm not trying to spot those. It's close enough, yeah. But it's 12 hours. So. We'll see.
I only.
Yep.
On every single, we find out. Would you look for?
I mean, my goal,
No, and.
I can probably do brains, how they want.
They wanted me to do it.
which one? Or the, technically it's still salary, so, but for the most part, Monday to 5. I got to be there a little bit longer.
He probably just had a bad.
Yeah.
Every 2 hours.
I don't know, I'll look at it.
Help them out. Has the anxiety like. Oh, man.
Oh, nice.
One of the guys I've known for years, and the other one, like we knew of each other. Like, yes. He's one of our better architects. Handsome looking. You were tomorrow. They get one G and they're over 20 years old. It's kind of like you know, what's not really learned the one I'm working on right now.
That's what I see.
Alright, everyone is able to use Proctorio, right? All at it, you've been able to add it to your, I'm sure all of you have been using it this entire time, hopefully. I just had a lot of issues with my last class being able to use it, and has everyone been pretty good being able to get on there?
I mean, we installed it and then that's it.
Never used any quizzes with it.
Like, but then nobody has told us anything. They said, oh, it's installed, it's there.
Yeah, it's like a one-time thing.
So you never have quizzes where you need to go on and take quizzes?
Oh, well, we go on the browser, which that has it installed, so it has to be on the browser.
But you notice your quiz looks different and Proctorio is looking at you and all that. stuff.
No.
It's saying that it's just an add-on.
Yeah.
It's like
They just
extension.
don't-
No, but I mean, have you taken quizzes where Proctorio is actually proctoring you? So
No.
what class were you in before this?
Scan that.
A scan, imaging.
Did they have no tests online?
They did, but like, yeah.
But nothing was-
Once, but it was right before he started using Proctorio, so it wasn't as people were still setting it up. So
We're
after
gonna have
that,
a lot of
we're,
issues with this, I can tell you right now. Hopefully everybody installed it correctly,
oh, that's because we're doing it at home, right?
and in here,
Yeah.
everyone's supposed to be using Proctorio, it's.
You can tell that we're using it.
Yeah, I mean.
In here, but I don't know about.
But when you get on there, you can't tell that it's monitoring you, it doesn't look at your, yeah, then you haven't been using it, so you're gonna be using it now.
Like, when you're going around the extension, it says it's on.
Yeah.
Well, let's try it. There is a pre-quiz that just opened. 20 questions, it's gonna, obviously, if you remember some stuff from physics 1, you'll probably get some of these answers right. Hopefully you remember some stuff, because that's a lot of this class. And, yeah, you got about 20 minutes, enjoy. Yes, yes,
Okay, yeah, so my computer doesn't download Proctorio.
gotta go get one from the front end. Have to figure it out, cause and every time we take them from home, it's mandatory to take them on Proctorio.
Password or?
Should be no password, as long as you installed it right, it just should go in there, it's gonna ask you to turn your camera on, all that good stuff.
Okay, let's see.
You need to allow all the permissions.
Oh, here, and now it's up. Automatically. Never cease.
Before you begin. Do all this. Your camera's on, looking at
It
you,
says something.
monitoring your every move, your eyes wander the wrong way, stop you and kick you out.
Allow on every visit.
Yep.
Okay.
Proctorio is watching.
Yeah, no, I-
Yes,
I'm asking for a password.
that means you don't have the suspension installed properly.
Yeah.
Ours won't go through the diagnostic.
I might need to be updated. Yeah, you can't take it on that.
It's important, right? Dude, this thing is cooked.
Who's not on it?
Brian,
Who's that?
I'm here on Zoom.
I know I can't.
How's it going? Are you dropping? Are you
Say-
in? Are you in the, can you not hear me?
I can't hear you.
Not at all?
No, I can't hear you.
So you can't hear me at all? Check, 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 check. It looks like the audio's on. I can see. Check. Yeah, it's showing. It's working.
I do hear your voice, but I can't understand what you're saying, like it's far away.
Are you in the? Sorry, I'll type first.
How do I know that?
You don't want to sleep close on your child.
If I'm standing here talking, can you hear me better? Yes?
Yes,
Okay, perfect. You have Proctorio installed
yes,
and it's asking you for a password.
correct.
Still asking you for a password? You have to update the what did you do?
Oh, I just changed my settings. Like, refreshed my page.
So what settings did you change?
I think I just pretty much just turn it off, turn it back on, just refreshed it.
Okay, yeah, turn it off, turn it back on, try to refresh it if you got Proctorio installed, and it should, like, it is, if all the settings are correct, it should allow you in without a password.
It's like everything's enabled. Everything's enabled for my, the edge. It's just not going through. So. Take a look at.
Might not have screen share permissions, go to system preferences, fix this.
And then are you have to check out for edge?
Are you on Edge or you on Chrome?
I'm an edge.
What's the number on Edge? Locked.
You can press the unlock button.
I don't know. It seemed embarrassing.
Is it allows thing
And showing and sharing. Firewall and stuff. That's off anyway. I think a lot of you will just have to take it later after you import IT to fix it. Hmm? Everything is on. Unfortunately, I'm not like a Proctorio expert. Obviously, he wasn't using it for your last class, otherwise it would be working. Because I troubleshooted this my last class and everyone who couldn't do it had to get IT. You have to download the extension. Search Proctorio extension. And another tab. And then you're using Google Chrome, so you want to download that. Bench up there. So, we try all the extension. So you all get together, so. We're gonna have it. You have to say that.
Bring issues to this.
You see?
Yeah.
Okay. If you can't, I'm gonna take off Proctorio for this one. But if it's not working for you, you need to get with IT this week because your next quiz is going to be with Proctorio. It has to be. So if you're having issues with it, you need to get with Costellum IT and sort it out this week. You won't let me turn it off once,
There you go.
once you guys have started. Maybe it'll let me once those of you who are on there are done. You know, whenever you're all. Is anyone still taking it? Okay, whenever you're all done, I'll have to. Turn it off at that point.
The damn page has become unresponsive. Well done.
Can you hear me okay? Alright. So SNR, scan time, and resolution, these are the three major, actually, I guess this is not a. Image quality parameter, but it is a major factor in overall quality of the study, right? Scan time, we don't want it to be too long. Resolution, SNR, we can talk about what those things mean. SNR is signal to noise ratio, right? This is how much signal we are inducing in, or how much current is being induced in the coil, divided by how much noise is being induced in the coil, right? It is a ratio. Anything to improve SNR will improve the signal or minimize the noise, right? So the analogy to that was like, I can either, if you're all talking and making noise, I can speak louder for you to hear me, or you can just quiet down and you can hear me, right? So a couple of different ways to think about that. Scan time, this one's pretty obvious. It's just how long is that scan? Resolution, what is that? This has to do with image quality too. So that is a very general term. What kind of image quality? What factor? That is, SNR has to do with graininess or non-graininess, right? Think about static, they call it, like in an old school TV, right? That's graininess too, right? That's noise. It's actually noise. Resolution. How well you can resolve something, right? How well you can resolve detail. Resolution has everything to do with being able to see fine detail or not, right? We have poor resolution, we can't see things very well. It looks blurry, looks pixelated, looks fuzzy. Those are all things that are those are all descriptors of what resolution might be. It either looks crisp, clean, clear, or fuzzy, blurry, pixelated, right? If we say it looks fuzzy, blurry, pixelated, we have low resolution, meaning our voxels are too big. Right? We want small voxels so we can resolve fine detail. SNR, if it is poor SNR, it looks grainy, right? Or noisy. If it has good SNR, we don't say it looks grainy or noisy, we say it looks good, right? So, and then scan time is obvious. Factors that control resolution, SNR, and scan time all kind of overlap a little bit. The scan time always uses how long is the scan. Does anyone remember the scan time equation?
Next times TR, that's about it.
You got half of the way there. Or actually at this point, you got a third of the way there because we haven't figured out the last part yet. We'll learn about that next week. TR times next time.
Phase matrix.
Phase matrix. Phase matrix. It's our matrix. Remember, our matrix is how many pieces we're dividing our field of view into. In each direction, we have a phase direction and a frequency direction. We could change those. How many? It's a grid, right? If you look back there at that calendar, that's a grid. How many pieces are we dividing that into in each direction? We're dividing into 1, 2, 3, 4, 7 in one direction and about 6 in the other, 5 in the other direction, right? If we divide it into more pieces, that grid would have smaller boxes on it, right? Those smaller boxes would equal smaller pixels. That would equal better resolution, right? Resolution is also controlled by phase matrix. What else? Frequency matrix. What else?
Slice thickness.
Slice thickness. And I'm not multiplying these together. I'm dotting them out here. What else controls resolution? Field of view. Size of the actual picture, right? Field of view, phase matrix, frequency matrix, and slice thickness control our resolution. SNR is controlled by a lot of things. SNR is controlled by your voxel size, right? How do we get our voxel size again? What was the equation for that?
Phase matrix times frequency matrix times slice thickness for the volume.
That equals our pixel area. Right? And then phase matrix, field of view divided by phase matrix times field of view divided by frequency matrix times our slice thickness equals our voxel volume. To get better resolution, I want my pixel area and my voxel volume to be what? Small, right? What does that do to my SNR though, if I have small voxels? It reduces our SNR, right? So to get better SNR, we want large voxels, right? But there's other things that control SNR too. Just remember, these are kind of inverses of each other. The smaller my voxel, the lower, or sorry, the smaller my voxel, the higher my resolution, but the lower my SNR. The larger my voxel, the higher the SNR and the lower the resolution, right? So it's a trade-off. Once again, we're trading in something for something else. We do this every day. We trade in exercise for health, right? We have to do the exercise, but we get healthy, right? Trade in, but it also costs time. We're trading in time too, right? That time equals money. We're trading in money too, right? There's all these different things, right? I go to work to trade in my time for money, and then I trade that money in for exercise equipment so that I can exercise and trade it in for health, right? Anyway, everything is a bunch of trade-offs in life and in MRI. So let's think about all of these things. SNR, what controls our SNR? Voxel volume, right? What else? What else controls SNR? TR does. Flip angle does. TE does.
Almost everything.
Our B0 strength, right? What else?
Coil selection.
Coil. And position, right?
Yeah.
And position. Remember, we want that coil to run parallel with B0 so that it is in the transverse plane, so the transverse magnetization cuts through it. What else affects SNR? Receive bandwidth.
An SA or an EX.
Right. Next controls band SNR. So look, some of these overlap, right? Voxel volume. Right here, right? Our phase matrix determines our voxel volume, or it's one determining factor of our voxel volume. So something that affects scan time also affects SNR and also affects our resolution, right? Next as well, that affects our scan time, affects our SNR, right? Does it affect our resolution? Not at all. Another one, rectangular field of view or phase field of view. Remember phase field of view, oversampling or undersampling in the phase direction. That affects our SNR. If we oversample, what happens to our SNR? Sampling more echoes, more data in K space. What do you think happens to SNR? It increases, just like NEX increases it. It also affects our scan time though, right? Phase field of view affects our scan time. If we oversample, we're going to have more scan time. Even though it's not part of the scan time equation, it actually affects how many phase encoding steps we are sampling. So it does affect our scan time. Does it affect our resolution to oversample or undersample in the phase direction? Does not. That is not something that affects our resolution. Think about it like adding pixels on the edge of an image, or think about it like cropping an image. If I take a picture and I crop it, I'm sure people have done that before, you crop the image, does that change the resolution? Does not. Doesn't change the resolution at all, just cropping it. Right? Anything else affect our SNR?
K space.
The amount of K space that you fill, which is controlled by your NEX, your phase field of view, yep. I think that's pretty good. There might be something that pops up. But we also have these other little categories off to the side here. There's some other things that I want to talk about. Those are the big three. But we also have contrast. I'm not talking about gadolinium contrast, I'm talking about image contrast, right? Also, certain artifacts. our contrast parameters again? What affects our T1 contrast? What controls the amount of T1 information we see? TR. Do you see TR anywhere else in here? Oh, there it is. Oh, right here too, right? So it's a trick that we know we're gonna be, if we're changing it, the TR to change our contrast, we're gonna be affecting something else somehow, right? What else controls contrast? What controls T2 contrast? TE, right? Do we see TE anywhere else? It's an R, right? Bless you. Some other things that affect contrast are TI. We'll talk about that later. That is going to affect certain things here as well. TR, TE are a major one. Also, there's one more. Flip angle. Do you see flip angle anywhere else? So up here in SNR, remember 90-degree flip angle with a long TR is going to give me the best SNR. I have to change my flip angle to change my gradient echo contrast. Remember, flip angle controls the T1 weighting in your gradient echo images. Then I'm going to affect my SNR. And then certain artifacts. We could say partial volume averaging or a lack of resolution can be considered an artifact. So we obviously know things affect resolution. What about chemical shift too? Remember chemical shift? Chemical shift is an artifact, right? There's also susceptibility artifact. Does anyone remember what controls the amount of chemical shift artifact that we see?
Bandwidth.
Receive bandwidth, right? You see that anywhere else over here? Up in the SNR area, right? So our receive bandwidth, if we change that to change SNR, we're going to be affecting chemical shift somehow. Susceptibility artifact is controlled by our TE and some other things as well, but we can either raise it or lower it with our TE. So SNR and contrast, right? So hopefully you're starting to see all of these things and how they're affecting each other by this. Let's go ahead and play a little game here and try to remember what does what. TE. Let's say our TE was 20. Sorry, let's say that it was 80. And we lowered it to 15. What happened? We lowered our TE. What changed in the image? SNR. What happens to SNR? It increases. Why does it increase?
More signal.
Because we reduce time.
SNR, remember TE controls how much dephasing we allow to happen before we actually collect the echo, right? So if we're allowing for, if we are allowing for a lot of dephasing with an 80, we're losing a lot of transverse magnetization, right? We lowered our TE to 15. Now we're listening back here. We have much more transverse magnetization by lowering our TE. We have more transverse magnetization. What do we have? More signal, right? So our SNR goes up. What else happened? Does anything happen to scan time?
No.
Nope. Not part of my scan time equation. Susceptibility artifact could potentially go down. We haven't really learned about that yet, but we didn't look, yeah, susceptibility artifact. So susceptibility artifact is created by having something in the machine that has a high susceptibility. Remember, all tissue, all material has some sort of magnetic susceptibility. Some of them Some tissues will actually change the magnetic field strength to make it weaker than it actually is. Some of them will make it stronger than it actually is. Some of them will not affect it much at all, right? We have diamagnetic, paramagnetic, super paramagnetic, and ferromagnetic. Ferromagnetic changes it a lot, right? It exponentially changes the magnetic field strength to where it is a magnet itself. It becomes a magnet itself, essentially, right? So if we have something in the machine like metal that has a high susceptibility, it's going to cause those areas to be either a lot stronger or a lot weaker than they normally were. If you think about precession, right? Protons precess based on gyro-magnetic ratio and the field strength, right? If I have different precessional frequencies, I'm going to have loss of phase coherence very quickly, right? Remember, to get transverse magnetization, we need phase coherence. If I lose phase coherence quickly, what happens to my transverse magnetization? It goes away, right? And you lose signal. You essentially get signal voids. Has anyone seen a metal artifact in an image yet? What does it look like? There's a dark area and you see warping, right? That's because there's dephasing of all of these, and also, yeah, dephasing, the frequencies completely go out of whack. So when we spatially encode, we get a big hole in the image. Now imagine, if I listen back to the echo quicker, is more of that dephasing or less going to happen? Less, right? Therefore, the susceptibility artifact. Is it a C? Anyway, susceptibility artifact goes down, right? What happens? What else happens? What does TE control as far as contrast?
T2.
T2 contrast, right? What happens to our T2 contrast by lowering our TE? Does it go up or down?
Down.
It goes down. We're eliminating T2 contrast by allowing for less dephasing. This is fat and water. We have this with an 80 TE. We have contrast between water and fat. Low signal from fat, bright signal from water. We excite and we listen back right away. Is there a lot of there? No, a lot more signal, a lot less contrast, a lot less T2 contrast. We're gonna need to know this stuff. What happens if we take our TR and we decrease it? Let's say we were at 2000 and we went to 600. What are the effects of that? What are the trade-offs? I heard SNR. What happens to SNR?
Yeah, less.
Yeah, we have less SNR, right? Remember what PR controls. It's how much longitudinal recovery we're allowing, right? Before at 2000, we're allowing for more longitudinal recovery. Thus, when we flip back into the transverse plane, we're going to have more transverse magnetization, right? Lower it to 600. Flip again, much less longitudinal magnetization to flip into the transverse plane, right? So before 2000, flip. 600, flip, right? Which one had more transverse magnetization? 2000, right? So our SNR goes down. What else happens here? I heard scan time. What happens in scan time? Scan time goes down. Right, that one's easy. The number in my multiplication problem goes down, then the total number is going to go down. Anything else happen? What kind of contrast does T1 or TR control? T1 contrast. What happens to T1 contrast? We get more T1 contrast, right?
Yeah.
Once again, recovery. If I wait for 2000, right? And then I flip again, water and fat are going to be much closer together than they are if I only wait 600. Remember, fat recovers quicker than water. If we flip at 600, we're going to have bright fat and dark water, right? So lowering our TR raises my T1 information or my T1 contrast. Anything else happen?
Number of slices going in?
There it is. Number of slices available. Goes down. Remember multi-slice acquisition? Here's my TR, right? Multi-slice acquisition states that I have to excite every single slice in the stack at least once. Collect one echo before I go and start over again, right? So this case right here, we have room for a second, room for a third, room for a fourth, and then we got to go back to the slice one, right? So in this case, with whatever TR that is, right, it's actually time, not distance, but there's, just to illustrate it, right, there's a certain amount of time we wait. We can scan with this particular TE as well. We can excite and refocus 4 slices before we have to go back and do slice one again, right? So if I wanted to get a 5th slice, what would I have to do to the TR? I would have to increase it, right? So by decreasing my TR here, my number of slices available to me went down, right? Receive bandwidth. First of all, what is receive bandwidth? Word, couple words.
The current, well,
That's how we create it. Receive bandwidth is the amount of frequencies are being sampled during echo collection. Right? So remember, an echo is forming. We need to collect data to store it into K-space to form an image. We have to collect a lot of these echoes, right? So excitation, refocusing, echo collection right here. We have to collect many of these echoes to fill in K-space to create an image. The amount of echoes I have to collect is determined by my phase matrix, also my phase field of view. And how many lines of K-space are we gonna, or how many times are we gonna fill each line of K-space? That's determined by NEX. Remember, number of signal averages. When we are collecting these echoes, we turn on a gradient to create a range of frequencies in the frequency direction so that we can spatial encode, which is something we'll talk about today. Right? We need to know where the signal's coming from. If not, let's say this was a 1 Tesla magnet right here that we're in. If I didn't turn a gradient on and we just turned on my receive coil to collect this echo, what frequency would I be recording?
42.57.
So 1 Tesla magnet, turn on my receive coil to all that signal coming back would be at what frequency? 42.57 megahertz, right? Is that a bandwidth? Is that a range of frequencies?
No.
It's not, it's one frequency, right? That means that everything across the field of view is at one frequency. That means whatever's over here looks the same as whatever's over here and whatever's in the center, right? They all have the same frequency. I don't know what is where, essentially. I don't know what voxel has what frequency. So to get a range of frequencies or a receive bandwidth, we turn on a gradient in the frequency direction during echo collection. That gradient now changes the magnetic field strength across distance, right? Now we have a range of frequencies, not just 42.57, we'd have lower frequencies on the low end and higher frequencies on the high end and all the frequencies in between. That is our receive bandwidth. That make sense? If it's not yet, don't worry, we'll talk about it more today. What happens though if we raise that receive bandwidth? Think about what happens to the gradient. It's steeper, right? If I want more frequencies from here to here, I need to turn on the gradient. I need to make it stronger, change the magnetic field strength across that same distance, right? So if I up my receive bandwidth, the gradient power increases. Right? The frequency encoding gradient. What else happens as far as parameters and trade-offs? That's a physical trade-off. What happens to SNR? Anything?
Down.
Increase.
SNR goes down. Why does it go down? Yep, it actually has us sampling more noise. Since we're sampling a larger range of frequencies, we're sampling more noise because noise exists at all frequencies. Right? Does it change our signal to increase bandwidth? Does it change the amount of signal we're sampling? Does it change our transverse magnetization? Not at all. It changes the amount of noise we're sampling, so our SNR goes down. Does anything happen to resolution? Nope. Does anything happen to contrast?
No.
Does anything happen to our chemical shift artifact?
Yeah, it lowers the chemical shift.
You're right. It lowers chemical shift. And we'll have a full lecture about that. But essentially, fat and water at a 1.5 Tesla magnet processed at about 224 hertz different from each other. Right? If I have a range of frequencies and fat and water both exist at the same spot in reality, by fat and water in the same voxel, fat is going to be moved down the gradient 224 hertz. That's chemical shift. So if I increase the bandwidth and I get more hertz closer together, fat and water won't shift apart as much. Decreasing our chemical shift by increasing the bandwidth. Also, our sampling rate how fast we sample all the data goes up. Meaning, our sampling time or our sample window. Think about that. I'll draw out this echo again. We have to collect data, a certain amount of data points. So when we're listening to this echo, when we turn on the receiver coil, the machine has to sample this echo a certain amount of times. The number of times we sample this thing is determined by the frequency matrix. Data points sampled in K-space. We'll talk about K-space in more detail though, but this is our data points sampled is determined. So if my frequency matrix is 320, that means we have to sample this echo 320 times. Our received bandwidth directly affects how fast we can sample those data points. If I have a higher bandwidth, I can sample 320 data points faster than I can with a lower bandwidth, right? So sampling rate goes up, my sampling time goes down. And if you're having a hard time seeing that, think about driving here from home. If your rate goes up, it takes you less time to get here, right? So that's what's happening there. If my sampling window goes down, that means I can listen to the echo faster. Right? So think about this. Multi-slice acquisition. If I can listen to my echo faster, I can decrease my minimum TE available. Right? So minimum TE or minty. Minimum TE goes down. And since my minimum TE goes down and my echo window goes down, I can start my next slice faster, which means the slices available to me goes up, right? A lot of stuff the bandwidth does, right? A lot more than we thought of before. But don't worry if you're not understanding it all yet. Hopefully you will by the end of this lecture. There's a lot of other parameters, right? Let's do one more until, and then we can start the lecture. Has nothing to do with today's lecture. Well, some of that did. You wanna do good? Keep listening. All right. How about this? Frequency matrix goes up and then we'll do phase matrix goes down. What happens if my frequency matrix increases? So think about what that means. That means I'm going from like maybe 224 to 320, right? That's an increase of my frequency matrix. What are the results or the consequences of that? Resolution goes up, right? My pixel gets smaller. Pixel gets smaller, resolution gets better, right? What else happens?
SNR goes down.
SNR goes down. Not as many protons can fit in those little boxes because the boxes are smaller, right? Anything else happen?
Longer acquisition time, I think.
You're right. My acquisition window or my sample window, like we just talked about before, so how long am I sampling K-space? Increases. This could sampling window or acquisition window. Right? And that makes sense. Remember I was saying before, we have to listen to that echo for a certain amount of times. I only have to listen to it for that many times versus, right? Gonna push that echo out further. Anything else happen? That's about it. This could also affect how many slices are available to you, right? If our acquisition window goes out, we have to listen to the echo for longer. We probably don't have as many slices per TR. And in that case, you're gonna have to raise your TR and your scan time might get longer. That's what happens when we add slices or we increase our frequency matrix. So any of you, are you guys at sites yet? Yeah. If you see your text changing the frequency matrix and it changing your scan time, it's because your acquisition window is changing, meaning that more slices are available. Well, sorry, say they decrease their frequency matrix and the scan time goes down. That's because more slices are now available in a shorter period of time. So the reason that scan time gets shorter is because the TR decreases. It's on auto TR and I guarantee you that TR goes down. That's the reason your scan time gets shorter. Because now it used to take me this long to fit 10 slices. Now changing the frequency matrix, meaning we can sample the echo faster, I can fit 10 slices into this amount of time. So the scan time got shorter because the TR went down. It has nothing to do with the frequency matrix. It has to do with how that affected your TR. Because remember, our scan time equation is TR times phase matrix times next, right? But our TR affects how many slices available. And I can't just make the patient's anatomy smaller. I still have to get through that many slices, right? So anything that can allow me to get that many slices in a shorter period of time will allow for me to decrease my TR, making the scan time shorter overall. Phase matrix, I decreased it. So I went from 224 to 192. What happened? Resolution gets worse. Voxels get bigger, resolution gets worse. So what happens to the SNR? Goes up because the voxels are bigger. Anything else happen? Scan time goes down, right? We're collecting less echoes per slice, so we don't have to go through as many TRs. Ready to go home yet? Let's take a little break and then we will start the lecture. Unless there's any questions, any specific parameters you want to go over, or any specific parameter questions? This is all important. You're going to start seeing this stuff. You're going to watch your text change things and be like, what's happened? What happened there? You're going to know, but you're like, oh yeah, that's what happened. Right? You want to be able to make those changes and those adjustments. And when you do, know what's going to happen, right? All right, let's come back in at 10:15. Yeah. 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 They look good, they're actually pretty good class, they, yeah, no, they're 40, it started like 48, but I think by the time it was over, there was like 43 of them. Not that that's a huge difference, but. They definitely, a lot of them that were trying really hard. Just a lot of extra work for me though. Yes. As long as you understood the grammars and trade-offs.
Okay. Get to that,
Yeah. Hopefully no later than 2.
Okay.
That's what I'm about to leave at, I don't know. Yeah.
I think of the name like that. Maybe. Thanks. That's not right there. I don't even think. You tend to do well, yeah, like, geez.
Monday, Thursday.
How you doing, Dan?
Looking for leads, do these are too good. Minutes.
I gotta give him her something done. Still.
Yes, so I'm going to use my captain class.
Yeah.
Where's Saturday? Monday,
Yeah. Oh, for my regular job, I'm doing 6 to 6.
Yeah. Yeah. I don't know. I think I'll put it in pages.
But it's nice because like typically I'm not there by myself and they don't know anything about it. Yeah. Yeah. Conveyor belt. It's like jazz.
I gave one.
Oh, you have
Let's say.
Oh, my sister. What is that right now? Beverly Hills. I will say it was.
Yeah.
It's 2 miles up the road.
Did you get my hair schedule?
Yeah. And they let me like from 4 to 9.
No, like I'm.
Well, what about Carnival?
Anytime I go to work. And then, so it could be like I'll leave the house like at 4 in the morning, or I think on Monday I have to leave like at 3. I'll leave vacation, and then there's also, I have time, we didn't have it.
Yeah. All right. Let's start this.
You don't like it? Not when you're starting, but it's fun.
All right, there is a Imaging U. Yeah, an Imaging U module to do, so make sure you get it done before next Friday, quiz and all. I'm not sure if there's a discussion forum, there probably is. There's 3 of them. Yes, a lot of work, but this is a lot of work to understand, right? So just do the work. They're all for you. It's not busy work. It's to actually focus on it. The only way you're really gonna understand it is if you practice. Right? Writing it out, practicing. Thinking about it is practicing. Going through these modules is practicing. So. Spatial localization. We have to know where these voxels are located, right? First of all, we have to know where the slice is located. We can't just excite everything at once, right? We have to excite just the slice. Or if we did excite everything at once, we have to figure out which slice within that volume we're looking at, right? So we have to do that. We have to figure out then, once we have a slice, we have 2 different dimensions, right? If this is my slice right here, I have, it's a coronal of my face. What directions do I have in that picture? Right to left and superior and inferior, right? So there are, first of all, you have to figure out which slice that is in this direction from anterior to posterior, right? So that's one dimension. Then you have to figure out where each individual signal is coming from in this direction and in this direction, right? So that's two more directions. It's three-dimensional space that we have to deal with, right? Spatial localization, that's why it's called that. Each voxel of tissue has a signal intensity. That signal intensity is based on the relaxation times and contrast parameters, and also the size of that voxel as well, right? Each voxel must be represented by a pixel, a picture element in the MRI image, right? So we're not really looking at 3D images, we're looking at 2D images. Even though we do 3D data collection, and we'll talk about what that is, we're always looking at a 2D picture, right? We're not looking at these 3D images yet. They're not coming out and we're spinning around in 3D space. We're looking at a 2D image, right? So even though we obtain data from a three-dimensional volume, because every slice has a thickness, it gets projected onto 2 dimensions and we see it as a pixel. The pixel must represent the voxel in size, shape, and location. We need to know where it's located, where it's coming from, and how do we figure that out? That's the details in here. How do we take a 3D object and display it as a 2D image? We create slices. Has anyone yet, I think I've mentioned this in Physics 1, but has anyone been to the Bodies Museum ever? The reason I like making that analogy or telling you about this is because there's a axially cut cadaver and it's spread out like across maybe 10 or 15 yards. And each one of those axial, I am, yeah. Never stop. Each one of those slices has a thickness when you're looking at it. Right? And to me, when I saw that, I was like, okay, yeah, that makes more sense. Because when I was first learning this, it didn't make sense why it would have a thickness to me. I was just thinking you cut open the body and you looked in it. Right? You're just looking at the body. But no, you're exciting a chunk of tissue, which makes sense because we're exciting hydrogen protons, right? You can't excite an infinitely thin slice of hydrogen protons. It has to be some sort of volume that you were exciting. So that's where our slice thickness is, and then we project it onto 2D space. We create these slices from a volume of tissue. Hopefully everybody can understand. I'm gonna grab this for just a second. This could potentially be our picture, right? But look, it has depth to it too. It has a thickness to it. You have to excite a certain chunk of protons to create an actual slice. Or to create an actual image, I should say. Within each slice, we have to put these tissues in the correct location in the image. To think about it, our field of view divided into frequency and phase. We have these little tiny squares, and each one of those squares has a particular amount of signal. The more signal they have, the brighter it manifests on the image. The less signal they have, the darker it manifests on the image. So we have all these gray scales, black and whites, and they all have to be arranged in the proper area so they look like a picture. We need to know where each one of those voxels is located, and we do that using spatial localization. All the details we get to come, but we need to understand K-space first before we get into this. We talked about it briefly, but we will talk about it in more detail now. This is an image, and this is K-space. This is the K-space of this image, right? So a couple things you want to look at here. This looks like nothing to me, right? It looks like a bunch of dots, essentially. What do you notice? You notice it's brighter in the center. If you look at this closer, you notice there's like some actual like patterns in it too, right? Yeah, it's essentially a digitized version of the echo. So we're going through and we're taking data points of that echo, and however the signal comes across at the time gets represented as this little grayscale across here. Each row of little dots or data points is each echo that we collect. So you can see we have a whole bunch of different rows of data points or echoes that we're collecting, right? And then a lot of different data points that we collect across each direction. Couple things I want to show you here. This area right here does not equal this area here. The data from here does not mean it's this information. In fact, every single line of K-space being an echo comes from the entire slice. So this information here was an echo from the entire slice. Same with this line. Every single part of K-space gives me some information about the entire image. So people have a hard time saying that. Let's say we took out this little piece of K-space. A lot of people think, oh, that's gonna be this little part of the picture right here. It's not. It's gonna give us some information about this entire image. So keep that in mind. Raw data. What raw data are we talking about? We're talking about echoes. We're essentially talking about an analog signal, right? Because remember, when the transverse magnetization is processing through the coil, right? It's spinning through the coil, it's creating alternating current. Different frequencies of current, of alternating current, that is essentially just an analog, it's like it's like a pulse, right? And we're taking that pulse or that signal intensity and we're digitizing it with data points. That's all we're doing. This is a diagram of K-space versus what K-space actually looks like. The diagram helps us kind of understand it because you can see here echoes, right? These look more like echoes than this does. Right? These aren't going to look like echoes because it's a digitized echo. It's sampling data points that are mathematically equivalent to an echo. So different ways to look at it, right? If I look at that, I'm not going to see these echoes, but it's important when you're looking at the diagram, you can see, oh, I have higher amplitude echoes in the center. You can see the amplitude is higher. What does amplitude, what does that mean as far as voltage or the strength of the echo? If you have a higher amplitude echo, that means that you have more voltage, more signal is there, right? Lower amplitude that we can see up here, there's less signal. And there's a reason for that. We'll talk about why that happens. You can see on the edges, on the ends, there's lower amplitude echoes, meaning not as much signal coming through and much higher amplitudes, a lot more signal in the center. You can kind of see that here too, right? That's brighter in the center. For every line of K-space, every line of K-space is an echo that we collect with a different amount of phase encoding. We'll talk about what phase encoding is and how we do it later on in the lecture, but that's essentially what it is. We encode each echo with a certain amount of phase shift. How do we do that? With a gradient, but I'll talk about that a little bit later. Remember, each one of these, that is why the amount of echoes that we collect is equivalent to the phase matrix, right? Our phase direction or our phase encoding direction requires us to collect a different echo from that slice with a different amount of phase shift. So if my phase matrix is 192, that means I have to collect 192 echoes from that slice, and we have to apply a different amount of phase encoding to each one of those echoes. So just keep that in your mind for now. We'll talk about what that actually means in a second. The amount of echoes we collect corresponds then with the phase matrix. Therefore, the amount of echoes that we collect in a given field of view corresponds directly to our resolution in the phase direction, right? So the more, if I have a small field of view and a lot of echoes, I have very tiny voxels, right? So the more echoes I collect in a given field of view in the phase direction, it's going to give me more, it's going to give me more resolution in the phase direction. Just like saying this, like let's say I had 224 by 192 and I change this to 224, right? That means I'm going to collect more echoes now and my voxel gets smaller in the phase direction, right? For every line of K-space we collect, we also must sample a certain amount of data points. We were just talking about this earlier when I was showing you the echo, the sample, the acquisition window, right? Remember, I was putting my marker up there, we have to collect a certain amount of data points, right? And if you look at that K-space, you can see those little dots. How many data points do I have to sample? That's determined by our frequency matrix. So in this case right here, for the frequency matrix of 224, that means we would turn on our gradient and sample that echo 224 times. We would digitize that echo into 224 data points. Therefore, the amount of data points we sample corresponds directly with resolution in the frequency direction. Remember, every field of view has two directions, right? A sagittal, I have A to P and superior to inferior, right? I have to encode in each one of those two directions. I could change my phase and frequency direction. I could say my phase direction is going to be superior to inferior or anterior to posterior. You'll notice this on your scanners. It'll show you your phase. How many of you are on GE scanners? It'll show you your frequency direction. So it's, what is your frequency direction? And you choose. That means the phase direction is the other one, right? So if you're doing a sagittal and your frequency direction is superior to inferior, that means your phase direction is anterior to posterior, right? Those of you on Siemens, anybody? It's going to show you your phase direction. All right, they like to just switch things up. Anyway, that frequency matrix is going to determine how many data points we collect. What determines how many rows of K-space we fill or how many echoes we need to collect? Phase matrix, right? What determines how many times we have to sample each one of those echoes? Frequency matrix. And the more echoes we collect and the more data points we sample in each one of those echoes, the higher the resolution, right? And then the opposite is true. Every row of K-space has discrete phase information. What is phase again? What does that word mean? Yeah, so it's where something, in this case, we're talking about where the signal or where the transverse magnetization is in its cycle, right? We can talk about it as any given individual magnetic moment, or we can talk about the whole echo of its own. Remember, we talk about phase coherence. Protons being in phase gives us transverse magnetization. When they're out of phase at different spots at the same time, it means we have little transverse magnetization. So we can actually apply a different amount of phase or where those protons are at a given period of time to a whole echo. And we do with our phase shifting. If you look at it as a waveform, we're looking at a wave like this. Those two waves are in phase, right? They are at the same spot at the same time. This one, however, is at the opposite spot at the same time, right? These are out of phase while these are in phase, right? So we can actually shift an echo's phase, the entire echo. Where is it at? Where is that transverse magnetization at? And that is what we are doing to spatial encode in this direction. Every single echo is going to have a different amount of phase shift. Every column has a different discrete frequency information. Remember, when we collect the echo, we are also turning on a gradient. That gradient creates a what? Frequency shift, right? Or range of frequencies, also known as a bandwidth, right? We create a received bandwidth, creating a range of different frequencies, so that when we can sample it, we can take apart that information and prescribe a voxel discrete frequency information. K-space has symmetry. If you've noticed, so I was showing you before, there is symmetry on each side. What does symmetry mean? It means it's equal and opposite, right? So there is this side equals this side. It's a mirror image, essentially. Same with this. It's a top and bottom are mirror images of each other. And you can kind of see that if you look at it. If you look at this part right here, you can see that up here, the opposite of it. Because of that symmetry, and that symmetry is actually a function of the geometry behind it. If you think about an echo forming too, remember our echo comes into phase and then it goes back out of phase. That echo is a mirror image of itself too, right? So that is where that comes from here. And then the amount of different phase shift on each side, that's harder to visualize, but it's the same thing. But because of this symmetry, we can collect only a part of K-space and synthesize the rest of the data. You can mathematically interpolate, right? if I had somebody with half a face, I could put a mirror up to them and they look like they had a whole face, right? Weird visual, but see these, since these are mirror images of each other, we can synthesize the data. We do that a lot. Partial Fourier. This happens a lot in an MRI to make things go faster, right? If I don't have to sample all the data, my scan time's quicker, right? So that does happen. But if I don't sample as many lines in case there's as many echoes, I have less SNR overall. But this does happen. But every line of K-space must be filled in some way to create an image. So either we collect everything or we mathematically interpolate some of it. Has to be completely filled though. Otherwise, we're going to be missing data in the image and we're not going to have a complete image. Is everyone okay with that information so far? Let's talk about fast Fourier transform, or the FFT. It's a mathematical algorithm that dissects K-space into discrete phase and frequency information. In MRI, it assigns each voxel a discrete phase and frequency. Think about this. Think about when you had your stereo on and you turn up the bass. And the bass gets louder, but nothing else gets louder, just the bass, right? The reason for that is because fast Fourier transform is able to take out those low frequencies and up their amplitude. That's fast Fourier transform, it's happening, right? When you're hearing music, you're hearing a whole bunch of frequencies all at once, right? Your high notes, mid notes, low notes, and all in between, right? You are listening to a lot of different frequencies, a bandwidth of a lot of different frequencies, right? The fact that I can just turn up highs and leave everything else alone, or turn up lows and leave everything else alone, shows me that FFT is happening there. And it does. It happens with music, it happens with sound. It can also happen with the frequencies that we are sampling in MRI. So in K-space, remember, I have a bunch of different phase information, which we're also going to understand is as a pseudo frequency. Hopefully I'll get you to understand how that makes sense. Phase shifts over time actually equal frequency. That's how you describe a frequency. If I say 1 hertz, that's a frequency, right? 1 hertz is 360 degrees in 1 second, right? So it is 360 degrees of phase shift in over time in 1 second, right? If I go 2 in 1 second, that's 2 hertz, right? That's 720 degrees of phase shift over 1 second, right? So a frequency is literally just the change in phase over time. If we can dissect these complex echoes, which are a lot of different frequencies and phases, into different information, which we do with fast Fourier transform, we can then spatially localize. So what, brass tacks, what does the fast Fourier transform do? It takes our complex data in K-space, which K-space is a whole bunch of different frequencies and phases or pseudo frequencies, and it breaks it up into its constituent parts. Constituent is just all of the contributing factors, right? We have a lot of different frequencies and a lot of different phases. Fast Fourier transform takes this complex waveform and breaks it up into all the different pieces. Once we do that, we can then spatially localize because we can assign each voxel a discrete phase and frequency information, right? So think about it like Battleship. Has anyone played this game before? Each square on this grid has a unique label, right? It has to have a 2-part label though. This is A1, right? There are other A's, but only this one is A1, right? There is only one A5. There is only one E5, right? But to describe where these are located, we have to have 2 pieces of information. We have to have letter and number, or phase and frequency information, right? So remember in K-space, we have discrete frequency information, discrete phase information. And this is not related to K-space, or sorry, it's not exactly correlated 1-to-1 from K-space, because I said before, each line contains information about the whole thing. But when we take K-space, which is digitized frequency and phase information, or pseudo frequency information, we can pull it apart and assign each voxel where that image came from a unique phase and frequency number so that we know where it is now. Right? If I put my battleship here, I can describe that with E8 through H8, right? Now we know where it is, as opposed to just being mixed up randomly in space. Because when we're getting all of that information from each echo, we have all of that information at once. Okay, so how do we take all of that phase and frequency information from K-space and break it apart? Fast Fourier transform, right? And why do we break it apart into discrete phase and frequency information? So that we can assign each pixel a unique frequency and phase value. Remember, all the pixels on this side are going to have the same range of frequencies if this is my frequency direction. And all the rows across this way are going to have the same phase information. Is that not enough for you? Hopefully not, because here comes the detail. Who was the godfather of the gradients? Remember his name? Who invented the gradients? Paul Lauterbur. Right, Paul Lauterbur. And why did he invent the gradients? So that we could spatially localize. That's the reason for all of that noise, is so that we can figure out where this information is coming from. So let's talk about the gradients again. Physical gradients. We have 3 of them, right? 3 physical gradient pairs. The X pair. X is, if somebody is laying down supine in a closed bore magnet, or a, we don't call it closed, but we kind of do. This is, the X gradient is the right to left. The Y gradient would be A to P, or top to bottom. Or yeah, A to P. Z gradient would be superior and inferior, or the edges of the board, right? Those are our different gradients. What do gradients do again? They create change in magnetic field strength. And how do they do that? By current, direct current in opposite directions of loops of in the coils, right? On one side, I have current running, and that's running in the same direction to where it's adding to the magnetic field over here. So it increases the strength. On the other side, it's running in the opposite direction to decrease the strength of B0. We have a linear change of field strength across the distance, right? That is what it's doing. And we could change that. We could switch the direction of the current to where now this one is adding to B0 and this one is subtracting from it. So we're just creating a change in magnetic field strength, a linear change, meaning it doesn't just go up and then down and then up again. It changes linearly, goes from higher to lower or lower to higher, whatever direction we decide, or the machine decides, by passing current in opposite directions through loops of coil, or loops of the coils. The magnetic field is created perpendicular to the loops, right? So if I have loops going in this direction, my magnetic field goes this way or this way, right? So here we go, current moving in opposite directions. This is just indicative of the field strength. In the very center, which we call isocenter, it's B0. 1 Tesla, or whatever your field strength is, 3 Tesla, whatever it is, right? As we move in this direction, B0 gets stronger. 3 Tesla goes to 3.1, 2, 3, 4, 5. As we go this way, from over here it goes 2.9, 8, 7, 6, right? So we have a linear change of field strength created by adding, superimposing magnetic fields over B0. Must be linear. We don't want this to go back down again. That's not going to give us a predictable change of field strength, thus not a predictable change in bandwidth, right? The gradient slope is proportional to the amount of current in the gradient loops, right? So the more current we run through the gradient coils, the steeper the gradient gets, okay? The greater the change of field strength over distance. Less current, shallow, right? That makes sense to everybody. Which one provides a higher bandwidth if that's my frequency encoding gradient?
More current.
More current. Steeper, greater change in field strength, say this is my field of view, right? Across here, greater change of field strength across my field of view. Thus greater range of precessional frequencies. Remember, precessional frequencies are directly proportional to your magnetic field strength, right? The magnetic field doesn't change at the exact center of the bore in all three planes. We call that isocenter. So when you landmark somebody, you're sending that spot you landmark to isocenter. Right to the very center of the magnet. Right? They might not be isocenter from on the y axis, right? Unless you prop them up a bit. But they are going to be an isocenter from in the z direction. They also might not be isocenter in the x direction unless you get them right in the very center of the table, right? But isocenter is the very center of the magnet in all three directions. So physical gradients perform logical functions. Remember, we have three different gradients. They have three different jobs to do in spatial localization. Those jobs are called slice select, frequency encoding, and phase encoding. This allows the MRI system to place each voxel of tissue in the correct place in the MRI image. Also known as spatial localization, right? So each physical gradient can perform any of these logical functions. It really depends upon the plane in which direction you choose as the frequency or phase encoding direction, right? Three physical gradients perform three logical functions. X, Y, and Z physical gradients can do any of these jobs. It's dependent upon your plane, sagittal, axial, or coronal, and which direction you choose as the phase and frequency direction. Right there. Which physical gradient does which logical job depends only on when you activate the physical gradient during the TR period. So I will show you when each of these is activated and why. We've all seen this before, right? This is our RF transmit. Let's say it's a 90-degree RF transmit. Remember, immediately we get RF receive back. We don't necessarily turn on the coil at that point. But if we did, we get a lot of current being induced in the coil right after excitation, right? There's a lot of transverse magnetization right there. And the D phase is due to spin-spin interactions, two star effects, all that good stuff. Right? And then we refocus it. And then when we collect the echo, we're receiving RF again, right? So this is RF transmit, RF into the patient. And this is RF being received back from the patient. In addition to that, all of these gradients are doing this stuff too. And this is a very minimal, basic diagram of what's actually happening. But it's showing you a lot more than we did before, right? Before we were just kind of showing you this and this. Now we can see all of this other stuff is happening at the same time. So the reason we show this is because it relates to this. What physical gradient does which logical job depends only on when you activate it during the TR. This is my TR. Let's say it happens again over here. When do I activate my gradients? Well, you can see they all activate at different times, right? Anyone guess what this means? Slice select. So our slice select gradient, you can see, turns on at the exact same time we are transmitting RF. PE, phase encoding. That gradient turns on sometime between excitation and refocusing. The exact time doesn't really matter, but it has to happen at that point. This one looks a little different, right? We'll find out what this means, but it's actually showing that we're doing it at different amplitudes each time we collect an echo, or putting a different amount of phase encoding to each echo that we put in K-space. And then our FE is frequency encoding. When is that one turned on? During echo collection, right? Giving us a range of frequencies, also known as a bandwidth. This is giving us our receive bandwidth. Or we could say our receive bandwidth determines the amplitude of this. We could say either or. Still following me?
Yes.
I heard one yes, we're good. Let's get through slice select before we take a break. Okay. The first gradient to be turned on is the slice select gradient, as you saw, right? This is the first gradient that is activated. And the reason for that is because we have to select a slice to excite. Right? That's the first thing that has to happen. We have to excite a slice. We don't want to excite everything. We want to excite just a slice of tissue. Otherwise, all the data coming back would be much harder to sort. Right? So the first spatial localization that happens is a slice of tissue is selected to be excited. This is done using the slice select gradient. Which physical gradient is the slice select gradient is dependent upon which imaging plane is selected. Axial, sagittal, or coronal. So how does this happen? We turn on a gradient. Magnetic field is different along all points of the gradient, right? So let's say it's 3 Tesla here, it's less over here, and it's more over here. Does anyone remember what this is? W boy. Wonder boy. Precessional frequency, or the resonant frequency, equals B0 times the gyromagnetic ratio. What is this equation again? Laramar equation, right? Our Laramar equation states that the precessional frequency will also be different at all of these different spots as B0 changes, or as the magnetic field strength changes, right? So by applying a gradient, not only am I changing the magnetic field, but by definition of the Laramar equation, I'm also changing the precessional frequency, right? What else do we call the precessional frequency? It's another term for it. The resonant frequency, right? Remember, to cause resonance, we have to transmit RF at the same frequency at which the protons are processing, right? So by doing this, we are basically creating a different resonant frequency across that distance, right? So now if I transmit RF at, let's say this is a 1 Tesla magnet at 42.57 megahertz, I'm only going to excite the protons right here. If I transmit at 42.8 megahertz, I'm going to excite only the protons over here, right? Starting to see what I'm doing here? Let's say this is, what's 1500 millitesla? What does that translate into? 1.5 Tesla, right? And let's say we're putting on a 20 millitesla per meter gradient. That's just showing you that as you move out a meter from isocenter, you're going to go up 20 millitesla. As we go in a meter in this direction, we're going to go down 20 millitesla, which it'll show you right here. So 20 centimeters over there, that's it's showing you what the millitesla would be. 20 millitesla per meter. So we go, 20 centimeters, sorry. Not a full meter. So if you divide that up, remember a full meter would be 100 centimeters. So it's essentially 2 millitesla per 10 centimeters as we move out. You don't need to know this math. It's just showing you that now we have different field strengths as we move across the gradient, right? In a certain distance, right? Depending upon the strength of the gradient. Also, at the same time, if we do the Laramar equation at 1.5 Tesla, our resonant frequency is 63.855 megahertz. As we move out, we can see that our resonant frequency changes, right? So each one of these areas along the gradient, or locations upon the gradient, has a different resonant frequency now. So now if I transmit RF at 63.684 megahertz, the tissue over here is the only tissue that will be excited, right? If I transmit at 64.025 megahertz, the tissue here will be the only tissue excited. You can almost say that I'm selecting a slice to excite, or slice selecting, right? Sorry. That is what is happening in Slice Select. We are turning on a gradient and then sending an RF at that resonant frequency perpendicular to B0 at the Laramar frequency that we created. If a gradient is activated, the magnetic field and precessional frequency will be different at each point along the gradient. Therefore, RF can be applied at a specific range of frequencies, and only the protons, the spins, or the tissue that is processing within that range of frequencies will be excited. A slice of tissue has been selectively excited at that point, right? Only spins processing at that frequency. Sorry, only the spins that are processing at that frequency correspond to that area of the gradient will be excited. We send an RF perpendicular at 63.855 megahertz. Only the spins in this tissue will be excited. Can you see that? For the gradient to do its job, though, it must be activated each time RF is transmitted, right? Let's say we transmitted RF, we wanted to select this size. Transmit RF at 63.769 megahertz. But let's say the gradient isn't on. All tissue then will be processing at 63.855 megahertz. Will this tissue get excited at that point? No, because it's not at that frequency. So for it to do its job, it has to be excited or activated at the same time that RF is transmitted into the patient, which is what you see in the diagram, right? Think about that as like a sheet of music or something, you know, it's timing, right? As you go across, certain things are happening at different times. You can see that Slice Select and RF transmission happen at the same time. Remember, in a spin echo sequence, we are transmitting a 180-degree RF pulse. So to refocus that tissue, that gradient is going to have to be on again. Which gradient is activated is dependent upon the plane, right? Axial slices, it's the Z gradient. People have a hard time visualizing this sometimes, but think about the direction that your slices are running, right? Axial slices are running either superior to inferior or inferior to superior, right? Which gradient is running in that direction? The Z gradient, right? So think about the direction that your slices are running. That is the gradient that is activated to perform slice selection. Which gradient is this? Z. My slices are running this way, right? That is how we are going to create a range of frequencies in that direction, or a different range of frequencies to only excite a particular slice, right? So our Z gradient performs slice selection for axial slices. Which direction, sorry, so let's say it's sagittal slices, right? Which direction are they running? Right to left. What gradient is that? That's the X gradient, right? So for sagittal slices, we're going to turn on our X gradient. And then Y, sorry, coronal is anterior to posterior. Which gradient is that? It's our Y gradient, right? So that would be the gradient that's turned on to perform slice selection coronally. Not seeing it? Which direction are my slices going? If this is coronal, which direction are we going? So this is my first slice. Where's my second slice? Right here, right? Third slice right here. Fourth slice right here. Which direction is that? A to P or P to A, right? And which gradient runs in that direction? The Y, right?
So we're focusing on the red line.
The red line would be like the slice, right? That is a coronal slice.
Brian,
Yes.
so when I had my lab, I don't know if you can look into Zoom. I'm gonna show you something. So when I did my lab, last semester, the instructor taught me something, it was really helpful. Doing your finger like this, just so you remember, it looks like this. Just so you remember what your slice direction. So this finger is your X gradient, left to right. This is your Z. Yeah, yeah. This is your Z and this is your Y for coronal.
So is this a Y, I guess? How-
The thumb is your Y. Your
Like,
middle finger
your
is your X.
You
Yeah,
label your fingers? Okay, I see down there.
goes like this. And then your X left to right, and then your Z anterior, posterior.
Okay.
I don't know if it makes sense to you guys.
I think it helped a lot of people. Thank you. So it's just, that's a technique to help you memorize, right? But to understand what it's doing is another concept, right? Once you know that which gradient is being activated right here? Which gradient is right to left? X, right? So which direction, if that's going this way, right? What slices are running this direction, or which slices?
Left to right.
Sagittal slices, right? So my X gradient is activated for slice selection for sagittal slices, right? For coronal, that's A to P, right? It's in this direction. Which slices are running in that direction if somebody is laying prone or supine in a magnet? Y, right? Those are coronal slices. So that Y gradient is used for slice select for coronal images. And like I said, once you memorize with that technique which way the gradients are located, just understand, look at visualize which direction your slices are running, right? Slices are running, coronal slices are running A to P. Which gradient is that? That's your Y, right? Sagittal slices are running right to left or left to right. Which gradient is that? It's your X. Axial slices are running superior to inferior. Which gradient is that? Z. You'll get it. Let's take a break before we do slides. Yeah, Let's be back by 11:45. I always like to start it like this after we get back from lunch, but I never get any takers. Actually, I do it a couple times. Anybody have any questions? Since you've been at lunch and been able to like think about it, but no questions? It's all 100% clear. Yes.
Okay, so for ScanLab, when it was phase and frequency, it would change the slice direction. Is it the slice direction or is it the entire imaging for phasing?
We'll talk about phase, but no, so phase and frequency direction does not change your slice plane at all.
Okay.
Yeah, phase and frequency direction just changes how you're spatially encoding in whatever angle you're, or whatever plane you're looking. Right? So once again, with the coronal, I can frequency encode superior to inferior or right to left. I can do either or, I can switch it, right? If I'm frequency encoding inferior to superior, then that means I'm phase encoding right to left, right? That means I can oversample from right to left, or I can undersample from right to left, because you do that in your phase direction, right? So, but then if you changed it to where it was frequency direction was right to left, that means your phase direction would be superior to inferior. That means you could oversample in this direction, right, or undersample. Means you'd also get phase wrap from down here up into your image, which means you have to oversample if you wanted to phase encode in that direction. Meaning we're typically going to phase encode from right to left if we're doing a coronal, because it's the shorter dimension. We'll get into all that in a minute though. So slice thickness. Remember, we have a thickness of the slice. It's not infinitely thin. We can change that. That's a parameter we can select. If we have a thicker slice, what happens to our spatial resolution? Say it again. Decreases, right? Thicker the slice, the more tissue is going to be projected into one voxel, right? Called partial volume averaging. If I have a slice that's as thick as my whole body, imagine what that slice would look like. You'd have every organ all being projected onto one plane. It would look just like a bunch of fuzzy mush, right? That's the technical term for it. So yeah, slice thickness is a spatial resolution parameter. For better spatial resolution, we want to go thinner with our slice, right? And during the slice select process, we can determine how thick our slice is going to be. Actually, in reality, we just select it on the graphic user interface, but the machine has to do something to create a slice that's either thicker or thinner, right? Thicker slice is going to give us more signal to noise, but it's going to lower our resolution, right? And the resolution we're talking about is through plane resolution. There is something called in plane resolution or through plane resolution. Does anyone know what a plane is? And it's a geometrical term, but what is a plane? Anyone know?
Basically, it's an X and Y.
It's a flat surface. It's 2 dimensions. A plane is 2 dimensions, right? So something that's flat, like if we're looking at an image, it's a plane, right? It's 2 dimensions. The planes, the fields are just a flat area is what a plane is. Through plane, through the plane, right? So if you think about slice thickness, if you have your image, it's through the slice, through the plane. That's why we call it through plane resolution. That make sense? Okay. In plane resolution is your other direction, which would be in the plane. Your through plane resolution is determined by your slice thickness. In plane resolution is determined by your pixel area, which is determined by field of view and your matrix, right? So slice thickness, it determines our through plane resolution. Controlled by transmit bandwidth and slope of your slice select gradient. That's how you determine your slice thickness. So that's how the machine controls your slice thickness. We've heard the term bandwidth before. It's usually called receive bandwidth though, right? Transmit bandwidth is different. Transmit bandwidth is the range of frequencies that we are transmitting into the patient. Right, so in the past, we've always said that like if it's at a 1 Tesla magnet to cause excitation, we're gonna excite at 42.57 megahertz. That's one frequency, right? It's not a range of frequencies. In reality, we transmit any range of frequencies into the patient. And the reason we do that is because we want to excite a range of tissue. And we have a range of tissue, we turn a gradient on because we have a range of perceptual frequencies that correlate with that tissue, right? Just by turning that gradient on. RF cannot be transmitted at a specific frequency. It's impossible to transmit RF at one frequency. An RF pulse contains a range of frequencies. This range of frequencies is termed the RF transmit bandwidth. So if we go back to this is RF transmit. The range of frequencies we use to transmit RF is our transmit bandwidth, right? The range of frequencies we listen back to is our receive bandwidth. Okay? So a couple things about transmit bandwidth. The narrower RF transmit bandwidth takes longer to transmit. It's easier to transmit a wide bandwidth. So a wide range of frequencies is much easier to transmit than a narrow range of frequencies. Narrow transmit bandwidths require a longer duration RF pulse. So it takes longer to transmit a narrower bandwidth as well. Obviously, wider transmit bandwidths are short duration RF pulse. We prefer to do things faster, right? So wider transmit bandwidth is probably would be much quicker, but there are some negative trade-offs to that. So I'll say this real quick and then I'll just draw it out so you can kind of see it. The steeper the gradient slope, the thinner your slices are going to be. Which gradient are we talking about? We're talking about our slice select gradient, right? And that is determined by the plane, right? So if it's a sagittal slice, our slice select gradient is what? For a sagittal slice? Which direction are my slices running? Y gradient, right? So for a sagittal slice, my Y gradient is going to be turned on. The steeper that gradient, the thinner my slice will be. The shallower the gradient, the thicker the slice will be. Steeper gradient slopes require more power, obviously, right? Than a narrower, a shallower gradient slope, assuming a constant RF transmit bandwidth. So take a look at this. Oh yeah, and then also on this side, the narrower the RF transmit bandwidth, the thinner the slice. The wider the transmit bandwidth, the thicker the slice. Narrower transmit bandwidths require more time to apply, assuming a constant gradient slope. So let me show you just a couple things to help you memorize this real quick. Thick slice, right? This is going to be achieved by a wide transmit bandwidth and a shallow gradient slope, or a combination between the two. So we're gonna have a wide transmit bandwidth, so we're transmitting, it's going to be a wide range of frequencies, and the gradient slope is going to be shallow. For a thin slice, we're going to have a narrow transmit bandwidth and a steep gradient slope. What gradient are we talking about again? The slice like gradient, right? Whatever, if it's a sagittal slice, yes, the Y gradient. If it's an axial slice, D gradient. It's a coronal slice, sorry, that's the Y gradient. It's the X for the sagittal slice. So, if you memorize this, that's okay. Let me show you why now. Narrow transmit bandwidth, it's sending in a narrow range of frequencies, right? As opposed to a wide range of frequencies. That one's easy to understand. The gradient slope is the more difficult to understand. So let me do this real quick. Let's say we turn on a gradient. At this amplitude, okay? And we transmit RF. So let's say this is a narrow transmit bandwidth. We're going to transmit from this frequency 2. That's frequency. Remember, when the gradient is on, it is causing us to have a range of precessional frequencies across the distance, right? So if I transmitted this particular bandwidth, I'm going to be exciting tissue from here all the way to here, right? Right? This is my transmit bandwidth. I'm transmitting from this low frequency to this higher frequency, right? And it's going to correlate with tissue from here to here. That would be the slice thickness I get, right? Now let's keep that same gradient slope and transmit at a wider bandwidth. Right? So now I'm going to transmit from this lower frequency down here to this higher frequency up here. Now I am exciting tissues from here, use a different color, from here all the way up to here. Right? If you think about tissue being in there, if this is a body in there, right? That gradient being turned on, if I transmit at a narrower bandwidth, only tissue in this small area will be excited, giving me a thinner slice, right? If we transmit at a wider bandwidth, tissue from here all the way to here will be excited, and the slice is thicker, right? Just like we said before, a wide transmit bandwidth will create thicker slices, assuming an equal gradient slope, right? Assuming the gradient slope doesn't change, right? So what do I do with my transmit bandwidth if I want thinner slices? Make it narrower, right? We don't change it, the system does. What does the system do? It makes it a narrower bandwidth. Remember though, narrow bandwidth is harder to transmit. So there's other things we can do as well. Can you see that? Right, we're just transmitting to if I have a range of frequencies, because I turn a gradient on, from here to here, transmitting at a narrower range is going to give me a thinner slice than at a wider range. Okay. That one's easier to understand than this one. Steep gradient. And a shallower gradient. Okay. Now let's transmit at the same bandwidth and see what happens. Let's say now my bandwidth is from here to here. So we will transmit across it. We will see where it touches each one of these gradients. Right there on this one. To about right there, right? So what is my slice thickness? With the steep gradient, it would be something like that, right? With that steep gradient amplitude. Now let's see where it touches the other gradient. It touches it here. All the way to here. Right? So with the shallower gradient, my slice thickness will be much wider, right? Because I am not creating such a wide range of frequencies across the distance, right? If I turn the gradient off completely, I have one frequency across all of the distance, right? So it doesn't matter how narrow my bandwidth is, it's going to excite everything, right? If I turn that gradient on just a little bit, there is just a very low bandwidth across a large distance. So even at a low transmit bandwidth, my slice would be very thick, right? show you, same thing is here with the. There's a graphic here on the PowerPoint, it might help you see this. Narrow bandwidth with a constant gradient slope, right? This is just showing you two gradient slopes at different times. Narrow bandwidth is going to excite this distance, right? Thinner slice. Wide bandwidth, thicker slice, right? Assuming a constant gradient slope. Now, two different slopes with the same bandwidth, right? Transmitting RF in from, remember, we have a range of frequencies now across this distance, right? Because we turn on a gradient. We're transmitting a range of frequencies in. It is exciting tissue from here all the way to here. That is a very thick slice, right? Now we're gonna send in the same narrow bandwidth, or whatever bandwidth it is, the bandwidth stays the same, with a steeper gradient, and now we're only exciting tissue from here to here. So what happens to the slice thickness? It gets thinner. So to get better resolution, I need to use steeper gradient slopes and narrower bandwidths, right? Both of which are harder to achieve. So to get good resolution, you are working your system to its highest capabilities. That's why we want to make sure that our systems have these high capabilities. What is your gradient slew rate? What is the max amplitude, right? These things affect our resolution. What is our RF capacity, right? User selects the slice thickness, and then the system selects the gradient slope and RF transmit bandwidth that balances gradient power, RF transmit power, and speed. And speed's important, right? This is all timing. We don't want our RF transmit to take a super long time, because then our TR starts to get affected, right? Or our minimum echo time starts to get affected. So how do we get thin slices? What does the system do? Yeah, if I had a slice thickness, of 10 and we lowered it to 5, what happened?
Narrow bandwidth.
Yeah, it's gonna narrow our transmit bandwidth. Remember, it's important to distinguish between transmit and receive. Transmit bandwidth is RF into the patient. Excitation, right? At a particular range of frequencies. What else is the system going to do?
Steep gradient.
Yep, it's going to give a steeper slice select gradient. Right? So remember, more power, longer time to do the narrower transmit bandwidth. Also, steeper slice select gradient is going to cause more energy to be running through those coils in opposite directions, right? Which will take longer for it to rise up. So going to narrower slices makes your system work harder, right? That's all. What do we do as technologists? We just write in a number there. But let's say I wanted to go from 5 down to 1 millimeter. My system might not do it. And it also might affect my minimum TR, my minimum T available by doing that, right? Also, I'm going to lose SNR. Another trade-off happening here, but this is just a system trade-off. Thicker slices, wider transmit bandwidth, shallower gradient slope, right? Thinner slices, steeper gradient, narrower bandwidth. If you can't visualize it, at least memorize it. This isn't that important. It's just saying that square, like profile, this will talk about, I'm gonna breeze through this. We'll talk about crosstalk and stuff later. Crosstalk is because our slice profile is typically not rectangular. We take more time to do this. And we can get some cross excitation. This is why we have gap in our slices. We don't want cross excitation or crosstalk. Because it affects the contrast of the image. So we won't worry about that yet. So there'll be nothing in your quiz about any of these slides. So we've talked about how to excite slices, right? That is the first thing we do. When does it happen? When does slice select happen? It happens the very first thing, right? It happens every time we transmit RF. So we transmit RF for excitation and in spin echo sequences for refocusing too, right? So every time we transmit that RF, that slice select gradient has to be turned on. Which gradient is turned on? It's dependent upon your plane, right? Your imaging plane. So know which gradient turns on for axial slices. Know which gradient turns on for coronal slices. Know which gradient turns on for sagittal slices. To help you remember that, it's the direction your slices are running, right? From one to whatever slice, that the direction that they're going is the gradient that is being turned on for slice select. The thinner the slice, the steeper my gradient is going to have to be, and the narrower the transmit bandwidth. The thicker the slice, the shallower the slice select gradient is going to be, shallower the slope, and the wider the transmit bandwidth. Should be pretty easy to memorize that stuff, right? Now that we have one plane, right, we've dealt with one dimension of three-dimensional reality. We have to deal with the other two. Once we have our slice that's been selectively excited, the tissues within that slice have to be localized in two different directions. The whole slice is excited every time. So how do we figure out where the different voxels are, the different pixels are in that slice? This spatial localization is called our in-plane resolution. So what affects our in-plane resolution? Our field of view and our frequency and phase matrix, right? This is done with our other two gradients. Our other two physical gradients to perform two other logical jobs, right? Two logical jobs being phase encoding and frequency encoding. Frequency encoding is also known as readout because it happens while we are sampling data. We're reading it out. So I'd write that down. Frequency encoding gradient can also be known as your readout gradient. I think they're the same thing, so you might hear them interchange with each other. So look at right here. We used a what gradient did we use for slice select in this? We used the Z gradient, right? And now we're going to collect an echo. We're going to put it in K-space. So now we have an image that looks like this. We have two different directions. What directions do we have? A to P and right to left, right? Which gradients then are associated with these different directions? What gradient is this?
Y,
Y gradient. And this is the
X.
So now we can do frequency encoding either with our X or Y gradient and phase encoding with either the X or Y. If we choose to frequency encode with our Y gradient, then obviously the X gradient has to be phase encoding, right? Or vice versa. You as a technologist can choose which direction you want to frequency or phase encode in. The first thing we will talk about is frequency encoding because it's easier to understand, even though it is the last thing to happen. So if we look on here, our frequency encoding gradient happens when? During echo collection, right? That frequency encoding is done by turning on a gradient which creates a range of frequencies across the distance, also known as a bandwidth, right? This is our receive bandwidth. If a gradient is energized, when the signal from the patient is being received, also known as when the echo is forming and we are collecting the data from the echo, what will happen? All points along the gradient will be received with different precessional frequencies, right? So if it's a 1 Tesla magnet, instead of receiving just 42.57 megahertz, now we receive a range of frequencies dependent upon the amplitude of that gradient, right? the signal from the patient can then be sorted into the different frequencies. What does that sorting for us? Do you remember from the beginning of the lecture? What can sort out the bass from the treble and the mids, the lows from the highs? Fast Fourier transform, right? So if we have a bunch of different frequencies across the distance that we are sampling, we can use fast Fourier transform to break it apart into its constituents again. We can sort it. And those frequencies relate to their position along the gradient. It gives us positional information based on the frequencies that they are processing at. So look at this. We turn on a gradient, right? This gradient is going from superior to inferior. We're using which gradient again? Sorry, it's anterior to posterior. Which gradient is that again? That is our y gradient. Anterior to posterior is our y gradient. We're utilizing that gradient. We are turning it on. On this side of the gradient, this is the high amplitude. We have higher frequencies, right? And as we move down, these tissues are processing at lower and lower frequencies. Center frequency at the center, and even lower and lower and lower and lower, all the way down to here. So each pixel in this direction has different frequencies, has a different range of frequencies, right? If I was to divide this into different blocks, which we actually do in MRI, right? Different rows of pixels, each row would now have a different frequency or different range of frequencies in this direction. Now we can tell the difference. We know that if we're getting signal back at high frequencies, we know it's coming from up here. The signal coming back to us that's at middle frequencies is coming from here. And the signal at the lower frequencies is from down here. Frequency at each point of the gradient is now different when we turn that gradient on during an echo collection, right? We have a range of frequencies now, and we know because we turned on the gradient in that direction, the system knows that the high frequencies are going to be over on this side, and the low frequencies are going to be on the other side, and all the frequencies in between can then be sorted where they are at in that pixel dependent upon the frequency that is received. The system collects all frequencies at the same time and sorts their signal according to their specific frequency, which is dependent on its position along the gradient. Right? Because the system knows, that's why we localize, or that's why we landmark. Put the person in there, it knows the position, at each position where that precessional frequency should be, dependent upon the amplitude of the gradient that it applied. So when it receives that signal back, we put it into K-space, fast Fourier transform can then say, oh, I'm getting a low signal from these high frequencies. So this area is black, right? Oh, down in the middle, I have relatively high signal, right? So this area is brighter. So it can sort the signal intensity in this direction based on its different frequencies. Think about a piano. If I lay out a piano, this direction, and you all close your eyes and I play a high C. Boop. Might not be a high C. I play that note, you know that I'm over here, even though you can't see me, because you receive that frequency, you know that that frequency is supposed to be over here, right? And then let's say you all close your eyes again, I played a low note. You know that I'm down here, right? That's the note that I'm playing. Now, if I play all these notes at the same time, just mix them all up, you could take them and put them where they need to be, because you know that that note is supposed to be where it's at along that keyboard. A keyboard is a bandwidth of audio frequencies, essentially, right? Piano is lows to highs. It's a range of frequencies, a bandwidth. There's a gradient of compression wave frequencies, essentially. Does that analogy make sense at all? How about this? I have all you sing low notes and all of you over sing high notes. Right? And I assign them all to you. And then I mix you all up in the room and you keep singing that note, I'm collecting it all at the same time. Then I sort you out. I know that the high frequencies are over here. I know that the low frequencies are over here. I can sit you back to where you belong based just on those frequencies, right? That's what's happening. Except for it's not notes, it's actual resonant frequencies. It's alternating current in the coil, right? But we can still measure its frequency by measuring the alternating current and how fast that is moving, alternating essentially. Once again, frequency encoding gradient is also called the readout gradient. So you will hear them interchanged. They're analogies for each other. Sometimes it's called the readout, sometimes it's called the frequency encoding. It's just the way it is in the literature. This provides spatial localization in one direction of the selected slice. Here's the keyboard analogy, right? Lower notes, middle notes, and high notes correlates with the lower end of the gradient, lower frequencies, and the higher end. So we know if this was a sagittal slice, right, and we were frequency encoding, sorry, if this was an axial slice and we were frequency encoding from right to left, we turn on the gradient, we know that over here there's going to be higher frequencies, and over here there's going to be lower frequencies, and they can be sorted where they're at spatially based on their frequency because we applied a gradient. Different frequencies across the field of view are created by the frequency encoding gradient. These frequencies look different, they're recorded as different from each other, so we can tell the difference between them. Frequency encoding is done during echo collection, right? So right here, during the echo collection, we turn on that gradient. Before we turn on that gradient, we only have one frequency, right? We just have whatever the Larimar frequency is at that particular field strength. Once we change the field strength across distance, we have now a range of frequencies. Having many frequencies helps us distinguish the difference between different pixels and where they're at across the field of view in that direction. The more discrete frequencies the system can discern, the better one voxel can be differentiated from another. So when we apply a gradient, there's basically an infinite amount of frequencies there, right? Because even from the number 1 to 2, we could break that into an infinite amount of numbers, right? We can go 1.000000001, 1.0000000, right? We can do that basically an infinite amount of time. So regardless of the bandwidth, we can break that into as many frequencies or as few frequencies as we like. All of this is saying is that the more frequencies we break that into, the more discrete frequencies we turn that into, the better, the more pixels we have essentially in that direction. Therefore, the higher resolution, right? And how do we do that again? Data points. The more frequency encoding points we collect, remember we go back to K-space, all those different points correlated with the frequency encoding matrix, right? The more points we collect, the more times we sample the echo, the more frequencies we can break that into. Therefore, the more pixels we have and the better the spatial resolution we get. But remember, all frequency encoding points are acquired simultaneously. We're acquiring them all at the same time. It just takes a certain amount of time to collect them so that we can take that echo that has many different frequencies in it and break it into as many frequencies as we would like. All frequency points for a slice are acquired simultaneously. It's like saying on the piano, I'm going to push all the notes down at the same time. And then I'm going to sample that. However many times I sample that is going to determine how many different keys I can put back on the piano. And then these are just different. It can be, this is an older PowerPoint, but do some of these numbers look familiar to what you've been seeing? On GE, there are certain, and even on Siemens, there's certain values, you're gonna notice they're always an even number. Because we basically, when you're cutting a field of view, you want just as many on the right side as you do on the left, same with top and bottom, so it's gonna be an even number. But you can, on more modern systems, you can pick different numbers than the pre-programmed ones that are in there. This is gonna go into sampling rate, we already talked about this. If you don't really understand all of the math behind this, it's fine. I'll give you the brass tacks, and I already talked to you about this. Our sampling rate is determined by our bandwidth. Like how fast can we sample data? And it's also determined by how many points we need to sample. We were already talking about this a little bit earlier, so don't let this scare you. The number of points we need to be sampled is determined by the frequency encoding matrix. So if my frequency encoding matrix is, right, let's just say my matrix is 320 by 224. Anyone seen that yet on some of their systems? That's kind of a common matrix in certain scans, depending on what you're doing. My frequency encoding matrix is always my higher number, right? So we want to divide that field of view into 320 pieces. In order to do that, we have to pull 320 different frequencies out of that bandwidth, that range of frequencies. And to do that, we must sample that many points. The system samples at different rates. So when you say rate, it's how quickly something is happening or how much of something is happening over a period of time. Right? When you drive here, when you drive at all, we're looking at your rate. Your speed is your driving rate. Right? It's how much of something is happening over a period of time. Miles per hour. Right? How many miles am I going for every hour? So that is a rate. The sampling rate here is how much data am I sampling, how many points am I sampling per millisecond, essentially, right? So it's something, you're collecting something over a period of time. That's the rate. Our sampling rate points are we sampling so that we can pull out these discrete frequencies over a period of time. The higher the sampling rate, the quicker I'm going to be able to sample data points, right? So the faster I will be able to sample these 320 points, right? If I increase my frequency matrix to 512, my sampling rate doesn't change, but my acquisition window changes, right? The time it takes to sample changes, right? Because now I'm still sampling at the same rate, but I have to sample more. But it's like if you decide to drive to your friend's house, it's further away than your house from here, right? You're gonna drive at the same speed, but you have to go further, so it's gonna take longer. Following me? So, all this is saying is that we will listen to the signal all together at once. It's a continuous waveform. We have to collect a certain amount of data points so that we can reconstruct that into smaller pieces. We can pull out the different frequencies. The system can sample at different rates, but has to sample the correct number of points. All right, Nyquist theorem. All of this is saying is that Nyquist theorem is saying that to correctly sample a waveform, we have to sample twice per cycle. And I will show you, there's some videos in Canvas that will show you this. If you sample less than twice per cycle, you cannot accurately determine what a waveform looks like. Right? I have to sample it at least here and over here. Here and over. I could sample more times or take pictures. Imagine taking pictures. I could take pictures many more times than twice per cycle. But if I only took a picture of this and then we didn't take a picture again until it got back, would we even know that it was moving? You would just see it here and then everyone closed their eyes. Open them. Did I move? Maybe. You don't know. Maybe I did, maybe I didn't. You only sampled once per cycle. Right? Now, say I did this, you open your eyes, you open them again. As long as you open them twice per cycle, you can predict what my frequency is. You can accurately predict. The same thing if I have a waveform like this. A cycle is from here to here again. That's my wavelength. I have to sample here and here twice per cycle so that I can reconstruct digitally what that wave actually looks like, that frequency looks like. We have the same waveform and we sample only once per cycle. When we reconstruct it, it doesn't look like a wave at all. Looks like nothing happened. Right? More than twice per cycle, we can connect the dots and we can still see the frequency, right? So Nyquist theorem. To correctly sample a waveform or a frequency, we have to sample it at least twice per cycle. You can sample more, but you can't sample less. This limits the sampling rate of the MR signal. So here we go. That's once per cycle, right? We reconstruct that. That looks like a straight line, doesn't look like a frequency. Poor representation of the waveform, that's undersampled. This is adequate representation of the waveform. We can sample more and still get the waveform. So what does Nyquist theorem state?
More than once.
You need to sample twice.
Yes, to accurately sample a waveform, or also known as a frequency, we have to at least sample twice per cycle. No less. We can sample more, but no less than twice per cycle. This right here is just saying that if we increase the sampling rate, we'll be able to collect data points in a shorter period of time. Like I was saying before. Let's say here's my echo. Let's say I have to sample 12 data points, right? I can go through and sample them at this rate. That took me a while, right? Because my rate was low. Or I can go, right? 12 data points much faster. Right? So if I increase my sampling rate, I can sample my echo. The amount of times I have to sample it depends on what? How many times do I need to sample that echo? Your frequency matrix, right? Whatever your frequency matrix is, determines how many times we have to sample the echo. How fast can we sample the echo? That is determined by our receive bandwidth. Because our receive bandwidth is also sounds like a frequency too, right? If I talk about a bandwidth, I'm saying things like 50 kilohertz. That means I have a range of frequencies from minus 25 kilohertz to plus 25 kilohertz across the field of view. That means I am sampling at 50,000 hertz. That is my sampling rate. Or I'm sampling at 50,000 times per second. Right? Because remember, a kilohertz is 1,000 hertz, right? So 50,000 hertz, remember, that's something happening at once every 50,000 seconds, right? Sorry, once every 1/50,000th of a second, right? That means I can sample at 50,000 times per second. That makes sense? How long does that take me to collect 12 or 320 data points if I can collect them at 50,000 per second? It's going to take me a fraction of a second, right? We can do the math. I'm just trying to stay away from the math, try to get you to understand. Let's say we raise the bandwidth to 100 kilohertz. Now I'm sampling at 100,000 times per second. I put an extra H in there. Right? If I can sample at 100,000 times per second, I'm going to collect these 320 data points at exactly half the time that it took before, right? So by raising the bandwidth, we can collect data much faster, meaning our sampling rate goes way up and our sampling time goes way down. It also works in reverse, right? So increasing our sampling rate will allow the samples to be taken in a shorter period of time. How many samples do we need to take? That is our frequency matrix, right? So if I increase my sampling rate by increasing the bandwidth, because of Nyquist's theorem, I can now sample faster. Decreasing the amount of time it takes to sample that 320, whatever data points we have. If I decrease the sampling rate, it's gonna take me longer because I didn't decrease the frequency matrix. I still have the same frequency matrix. I just need to take longer to collect it, right? How do I increase my sampling rate? Increase the bandwidth, right? That's why it decreases your minimum TE available and makes more slices available to you. Decreasing the sampling rate would be decreasing the bandwidth. So there is some math in here, so those of you who are math minded can see. Let's say we need 256 samples. What is my frequency encoding matrix in this case? Not a trick question. 256, right? If I need to sample 256 data points, that means my matrix is 256. That means we want to take that field of view and prescribe 256 discrete frequencies across that field of view. So that I have 256 different pixels giving me a particular resolution, right? Nyquist's theorem always has to be obeyed. Let's assume we have a 16,000 hertz bandwidth, which is 16 kilohertz. That means we are sampling 16,000 cycles in a second, which means our sampling rate, 16 each millisecond is how fast we're sampling in that case. So we are able to sample 16 data points in 1 millisecond. A millisecond is 1,000th of a second, right? So if you take a second and you divide it into 1,000 pieces, that's how long a millisecond is. Very short. We can't even experience because we're not sampling reality that fast, right? We humans aren't sampling reality that fast, much slower. How long then is it needed to sample 256 data points if it takes us 1 millisecond to sample 16?
16 milliseconds.
It's pretty simple math. Two points are every cycle, so 280 cycles need to be sampled, right? That means it's going to be 8 milliseconds sampling time. Now let's take that same thing. You guys won't need to do this math. That's why I'm kind of banging through it real quick. Now I have an 8 kilohertz bandwidth. What do you think? What happens to my sampling rate? So it goes down, right? My sampling rate goes down, meaning it's going to take me longer to sample this data, right? Now I'm only sampling 8 each millisecond. It's 8,000 cycles each second, meaning go through 8 cycles in a millisecond, right? How long would it take to sample 256 data points? It's going to be twice as long as it was before. 16 milliseconds now. Now my echo window is much longer, meaning my minimum TE is pushed out, right? Meaning my next slice cannot be excited as early. So brass tacks on all this is that as sampling rate decreases, the sampling time goes up. How do we decrease the sampling rate?
Decrease bandwidth.
Increasing the bandwidth, and the opposite is true. If we want to increase the sampling rate, we increase the bandwidth, right?
Yeah.
Longer sampling time means receiver coils and frequency encoding gradients are on for a longer time. Another thing though that increases your sampling time or decreases it is how many points you need to sample, right? So if I need to sample 512 as opposed to 320, even if my rate stays the same, my sampling time is going to go up because I just have to do more. I have to travel further, right? So a longer sampling time means an increase in minimum TR and TE available to you. That's where that trade-off comes from. We talked about bandwidth doing that, you know, increasing or decreasing, causing this, but that's why it happens. Isn't it exciting? It also has other important effects on image quality. So here we go, brass tacks on it. Receive bandwidth, that's the range of frequencies that are sampled. Does my receive bandwidth affect my resolution? Does it have any effect on how many pixels we have across the field of view in the frequency direction? Nope, not at all. It only affects how fast we can sample the data to create those pixels, right? Sampling rate, the rate at which the frequencies are sampled. Sampling time is the duration of the gradient activation and the receiver coils. We can set the receiver bandwidth, right? Sampling rate is equal to the receive bandwidth. So if my receive bandwidth is 50 kilohertz, that means I go through basically 50 cycles in a millisecond, right? So we can always calculate it. And sampling time is set by the system that's based upon your frequency matrix. How long does it take to sample however many data points we prescribe? Y'all hate me yet? I'm trying to make this as simple as possible. Right? Like I said, no math in this one. You don't have to worry about solving that. I just want you to understand what we're doing here. How are we frequency encoding? What are we doing to get pixels in the frequency direction? We're turning on a gradient. When are we turning that on?
Slice selection.
No. During the echo collection, right? When I'm talking about frequency encoding here, to get to spatially encode in the frequency direction, we are turning on a gradient during echo collection to create a range of frequencies across the field of view. We are then collecting a certain amount of data points that determines my resolution, right? How many pixels we want to reconstruct, or how many different frequencies we want to reconstruct in that direction. So if my frequency matrix is 320, I have to sample 320 data points during echo collection so that I can so that the fast Fourier transform can reconstruct 320 discrete ranges of frequency across the field of view. Right? And that gives us our resolution. How fast can we sample those points? Well, that depends upon the bandwidth, right? If we have a higher bandwidth or steeper gradient applied, we'll be able to sample those 320 data points faster. Lower gradient, lower amplitude gradient, lower receive bandwidth, we won't sample those data points as fast. By not sampling as fast, our minimum TE gets higher, so does our minimum TR. Once again, receive bandwidth is set by you. That's the only, you can set the receive bandwidth, you can predict, you can set the field of view, you can set the frequency encoding matrix, but nothing else is done by, it's all done by the system. Don't worry about the field of view and receive bandwidth. I'm gonna breeze through this. This just, basically all this is saying is that to get a, oh, don't even worry about this. There'll be no test on this. This is just gonna confuse everybody. If you want to know about this, you can find me later. This is basically all this is saying is that if I want a range of frequencies across the smaller field of view, my gradient has to be on at a higher amplitude. Essentially, that's all this whole thing is saying. If I want a larger field of view, a 50 kilohertz bandwidth is going to require a shallower frequency encoding gradient than if I only have like a 16 centimeter field of view. That's all that's saying. Let's take a 5-minute break before we go into phase encoding. If there are any questions about frequency going to your slice select, please let me know before we start phasing coding, because this is the hardest part. I'm not sure if this canvas can tell you. I think it's chapter 3 or 4. Five.
Come back, I was like, hold on.
I'm trying. So, what is my plan? I've been trying.
We have to use chlorine in this scan. She And then we have one more step, but they finish on. So they finish fast. So we just.
Oh,
Bree was about to bring it one, we said it was like.
Yeah.
oh, cool.
And she was like, and she's like, I'm gonna.
There is a video too, review of physics 1 and spatial encoding. I would watch that. It's a 15-minute video. It's in Canvas as well. There's also a Nyquist theorem one that might help you out as well.
She's kind of
I can do it.
I was only with her.
Cool. I think I like upset her just like. Little things. Little traits. That's why it's such a bad one.
We should have stopped. But I was looking.
I forgot my favorite name, so. It's a great, but you said really. Yeah, no.
No.
I was like, yeah.
Your little black.
I'm gonna try. I was just looking at very like. Anyway, so we came out. How awkward it was. So it's like, what, I have like, even so I got like halfway. I'm just like, how like, I got my trouble. I don't know what you have.
Did you go and find some?
No, I think I just left it on this.
There was actually a lot of traps.
It's the first Friday.
Oh, yeah, he's nice. And then say, I said, it's exactly what I said. Yeah, he's like, for them, so.
Okay, I'll check it out.
He is. That. He's very like, but yeah, he's getting a lot of. Oh, you got this feeling?
Well, you kind of say no for everything.
And you from there, yeah.
Makes them tired of
Warm it out, yeah.
Oh, where the bottom.
Yeah, I just keep.
No, I was gonna be like, they finally.
He does. Yeah, no, I.
Like a month?
Yeah. Right now.
And then something's like, if you like, create, so, okay, that's like.
Facebook.
This, yeah, we'll talk about
All the actual holiday. Yeah. Well, Thanksgiving is gonna be interesting, it's usually the entire weekend.
Yeah.
So. Hour.
It still doesn't get.
So.
They're really, yeah, they did.
It's been the. They already met. Or you have to do a minimum of 5 hours, or is it minimum of 5 hours? Wow. Well, that's gonna be. You need to do 7 days a week. Yeah, but if you're gonna- Well, I'm just saying, like, to stay on target 34 hours per week. Like, you're gonna have to make up hours on site then.
We ready? Does anyone want anything clarified or reiterated or gone over again? Or maybe I can explain it in a different way. Anything not making sense? Probably a lot of it.
We have to just rewatch it.
Yeah.
Yeah. Don't worry, learning doesn't happen right away. Watching this or listening to the podcast about it, most of the learning happens when you reflect upon it. So you gotta have that information there, and then you gotta just start telling yourself about it, and then you'll see what you don't know. And then when you sleep at night, it'll actually solidify it. So don't wait to go over this again, is my point. Try to go over it again right away. You're gonna get the most out of it that way.
I was gonna say, when I wake up, when I think about it, then I know I'm learning it.
Yeah.
I wake up and I'm like, right at night, then I'm like, whoa, my brain is absorbing it.
Yeah. So yeah, the learning process does not happen, it's not through osmosis and just like absorb it. I wish it was that way, we'd all just download it real quick and we'd be done, right? This class would be like milliseconds long, whatever your sampling rate would be. Alright, phase encoding, what is phase again? Position, right? Position of where protons are at in this case, or the signal in the case that we're talking here. We know when slice select happens, right? During RF transmission. That makes sense because we have to create a range of frequencies across distance in the direction the slices are running, so that each slice can have its own range of frequencies and be selectively excited. What does that mean to be selectively excited? To be excited only and not everything else, right? We want to make sure that when we turn on this gradient so that each slice has its own range of frequencies, so that we don't excite everything, we just select one. Right? Excite, refocus, collect its echo. If we selected multiple slices, we'd be collecting echoes from multiple slices at the same time, be contaminating this echo, right? Then something else happens. Slice select again, frequency encoding during our echo collection, right? The gradient is turned on. The amplitude of this gradient, or the size, the steepness of this gradient, is determined by what? The bandwidth. The receiver bandwidth determines the amplitude of this gradient. And the amount of data points that we collect is determined by what? How many data points do we need to collect? Our rate is at least 2 per second. It's frequency encoding matrix. Yeah. So our frequency encoding matrix determines how many data points we have to sample. How many times do we need to do that? How many times do we need to go through, excite, refocus, and collect an echo? We need to do that as many times as our phase encoding matrix dictates, right? Notice this gradient right here happening in between slice select and the other slice select. It looks a little bit different, right? Kind of looks like a weird inverted pyramid, or a pyramid and then an inversion. This is actually showing that each time we collect an echo, we're going to be applying a gradient in the phase direction at a different amplitude. Different amplitude and different polarity. So, excite, phase encoding. Refocus, collect the echo. Excite, phase encoding. Refocus, collect the echo. Excite, phase encoding. Like this. The gradient that is applied is at a different amplitude every single echo we collect. So how many echoes do we need to collect? If that is my matrix, how many echoes do I have to collect? 192. I have to collect 320 data points in each one of those echoes, right? That means I'm collecting each one of these 192 echoes. I'm going to apply 192 different amplitudes of phase encoding to each one of those echoes. Right? Meaning I will get a different amount of phase shift across the field of view in that direction, in the phase direction. Let's show you how it works. Slice select and frequency encoding are activated with the same amplitude in a given sequence, so it never changes. Our slice select gradient, the amplitude of this gradient is determined by what? What determines our slice select gradient amplitude? What parameter is going to affect the amplitude of my slice select gradient? That's something to do with that. I don't affect transmit bandwidth though.
No.
Something that I can put into a machine that is going to directly impact the slice select gradient amplitude.
Then receive band will be set by the tech.
Slice thickness, right? Remember slice thickness determined by the amplitude of the slice select gradient and the transmit bandwidth, right? So whatever my slice thickness is going to determine the amplitude of this gradient. Does my slice thickness change throughout the scan? The same slice thickness all the time, so this amplitude does not change. Frequency encoding gradient. Its amplitude is determined by what? It is turned on during the echo collection. What determines its amplitude?
Thickness.
The receive bandwidth, right? Amplitude determined by slice thickness. Amplitude determined by our receive bandwidth. Those don't change. They stay the same the entire time throughout that sequence. However, the phase encoding matrix is going to be different for every single echo we collect. How many echoes do we collect? In this case, 192, whatever our phase encoding matrix is. And how many lines of K-space are there? 192. How many times do I need to fill each one of those 192 lines? That's determined by my next, right? This is K-space. I'm going to collect 192 echoes, each of which have a different amplitude of phase encoding. What does that mean? That means at a certain point, somewhere in between excitation and refocusing, we're going to turn on the gradient and then turn it off. Then we're going to do it again. We're going to turn it on and turn it off. What does that do? That creates a range of frequencies across the distance, right? In whatever direction we decide is our phase direction. Let's just say it's a coronal of the face, and we decide to phase encode right to left. So we will blip on our, which gradient is this? X gradient. We turn that on. While that's on, let's say all the protons are processing at the same speed. Right, they're processing like this. I can't keep rotating my hands, but let's just say these are all protons in phase, going like this, right? Turn on the gradient, boom, like this. Higher field strength over here, lower over here, right? So these ones speed up, right? They start to process faster. And these ones over here process slower, right? Until we turn that gradient off. And then they all go into processing the same speed again, right? But now we have a phase shift that remains, right? With a high amplitude gradient, when we blip it on, these are going to speed up a lot more, and these are going to slow down a lot more, so we're going to end up with a large phase shift. Can you imagine what's going on there? These are all spinning in this direction, right? But these speed up, and these ones slow down. So we have a phase shift that remains, even though the frequencies go back to the same frequency once we turn the gradient off, right? That is a certain amount of phase shift that we induced intentionally. And then the next time we turn it on, it's not as steep, right? We turn it on here. That is going to get them to speed up a little bit, but not as much. And then we'll turn it off. Now we end up with a phase shift, but not as much, right? And then lower and lower. The lowest amplitude, we barely have any phase shift at all, right? And then it goes in the opposite direction as we move down into this direction, right? So we're going to induce phase shifts across the field of view in the phase direction. Each echo is going to have a different amount of phase shift. Every time we collect an echo, we have a different amplitude of phase encoding that we turn on and then turn off. Once we turn it off, the frequencies go back to the same, but we have a phase shift that remains, right? And since we stepped the gradient incrementally for every single echo that we collect, we do this fun little dance and we end up with a different amount of phase shift in that echo. Now every echo looks different, right? It has a different amount of phase shift. And that is activated once per TR period. Hopefully now you can start seeing why the number of phase encoding steps determines our scan time as well, right? How long does it take us to collect an echo? That's determined by our TR. How long does it take in between each one? How many echoes do we have to collect? Well, we have to collect as many as we need to get 192 pixels in our phase direction, right? So it could be because we have to have a different amplitude for each one of those, so we can get a different amount of phase shift so that they look different. Right? And then how many times do we do that? We multiply that by our next. So next is going back and doing it all again. Right? Each time the phase encoding gradient is activated, the frequencies along the gradient change. This changes the precessional frequencies as well, causing some to precess faster and some to precess slower along the gradient, inducing a phase shift. Once that gradient is turned off, which it is, the frequencies go back to normal, but the phase shift doesn't. It remains. Steep gradient, you can see all these phase shifts happen. I really don't like that graphic at all. But you can see here, right? We turn on the gradient. The ones over here will speed up, right? They gain phase. These ones slow down, so they're losing phase, and the ones in the center stay the same, right? So we have a band basically of phase shifts. This is the part that's hard to understand, but the FFT cannot directly detect phase information. It can only detect frequency information, but phase and frequency are related because a frequency equals change in phase over time. Like I was saying before, 1 hertz is 1 cycle or 360 degrees of phase shift over 1 second, right? 2 hertz is 720 degrees of phase shift over 1 second. Half a hertz is 360 degrees of phase shift over 2 seconds, right? So you can describe frequency by a change in phase over time. Therefore, if we make different amounts of phase shifts in different areas of the field of view over a period of time, we get something called a pseudo frequency. And that period of time is the TR. So this is, if you're not completely understanding this, it's okay. Try to demonstrate it though. Imagine this is our field of view, right? And our phase encoding gradient is this direction, right? We're gonna say we're phase encoding this way. We could phase encode superior and inferior, but to make it easier, I'm gonna phase encode in this direction. Let's say we have one, two, three, four, five, six rows. So our phase matrix is 6, just to simplify this. Okay. I'm just gonna break this into a row of pixels because they're all gonna have the same phase along this. So I'm just gonna break into each column will have the same phase. I'm just gonna break it into a row of 6 pixels. So what I'll do, pretend that field of view, I'm just pulling one out. Sure. So we're dividing into 6 pixels in that direction. Let's not go, well, actually, no, let's go in order. Let's say we turn on a phase encoding gradient like this. We blip it on, we blip it off, right? The amount of phase shift we have, we're gonna have a lot of phase shift over here. Let's say that's the amount of phase shift we have after turning on a steep gradient, right? Ones over here are gonna speed up, these are gonna slow down, we're gonna have a lot of phase shift. Record that echo. This phase is not recorded though. It is, but it's not directly recorded. The next time we do it, less amplitude, right? A shallower amplitude. we need to do this 6 times since we have to reconstruct 6 different pixels. This next one. Right? Not as much of a phase shift the next time, right? Next time. Less amplitude. And so on and so forth. I don't have many more colors, but right, imagine once I get all the way down to here, we're barely gonna have any phase shift right across. It's gonna be like this. Right? Can you kind of see what was happening there? So the voxels or the tissue on the edges of the field of view experience a greater amount of phase shift over each TR period than the ones in the center do, right? These ones barely changed phase over the same amount of time that these ones changed a lot of phase on each end, right? Because outside here, we're experiencing much greater changes in field strength than we are in the center, right? Out here, it changes a lot more each period than it does in the center, right? So we have a greater phase shift over each TR period on the pixels on the outside than we do in the center. This is change in phase over time, also known as a pseudo frequency, meaning that the outside pixels have a greater pseudo frequency or a higher pseudo frequency than the ones in the center do. And I will prove to you with this PowerPoint here that a greater change in phase over time equals a greater pseudo frequency. So let me minimize this. Bear with me. Okay, here. No frequency we're seeing at all, right? There's no frequency going on here. We just have the same phase over each one, right? Just a different change in phase, right? We just have phase. If we're just taking a picture of this right now, we wouldn't see any frequency, right? We would just see a change of phase. Another change of phase, right? If I play these together though, which one changes more phase over time? The one on the left has a greater change of phase over each picture we take, right? So it has a greater change of phase over time than this one does, right? If we play it together, they look like frequencies. Which one has the higher frequency? Yeah, the one on the left, right? Which one looks faster? The one on the left, right? Large change of phase over time. Even though it's just change of phase, there's no frequency there until we look at them one after another, right? Now we can see we have a pseudo frequency here. The greater change in phase over each individual slide, the higher the pseudo frequency is than the lower change in phase over time. Right? So that's what we're doing here. We are applying a change of phase. The tissues that are on the outsides of the field of view, not outside the field of view, but towards the edges of the field of view, are going to experience a greater phase shift in each subsequent echo, meaning they are going to have larger phase shifts over each TR, giving them a higher pseudo frequency than the ones in the center that have just a little bit of phase shift over the same period of time. So that is essentially what we are doing. We're not We're not looking at each individual echo as a different phase shift. We're looking at the tissues in that particular area having a great phase shift or a little phase shift over a period of time. And that is how we are creating those pseudo frequencies. So you can even see it here, steep gradient, shallow gradient. Notice which ones have greater phase shift. So imagine this is the field of view. This is an axial of the head. We're phase encoding right to left, right? The tissues over here are going to have greater amount of phase shift than the ones in the center view, right? So we can literally look at each row of voxels and say this one has a high pseudo frequency, this one has a lower, all the way down to almost no pseudo frequency, and then we go in this direction, it's the opposite pseudo frequency, right? And this is just, that's actually just showing here how phase shift over time, the lower amount of phase shift over time ends up being a lower pseudo frequency than a higher amount of phase shift over time. So how does this relate to K-space and where the data is put? Are you understanding this kind of what we're doing here? Each echo has a different amount of phase shift, right? That's what you need to understand. And how do we apply a different amount of phase shift? By applying a different amplitude of phase encoding. It blips on, turns off. That happens where? In between excitation and refocusing, right? How many echoes of K-space do we need to fill? What is it determined by? Our phase matrix, right? Therefore, if we are the amount of phase encoding amplitudes are going to be determined by our phase matrix as well, right? So how is K-space filled? The first echo we collect in a standard spin echo sequence is going to be with a high amplitude of phase encoding. That echo is going to go at the top of K-space. The next echo we collect, slightly lower amplitude. That is going to go in the next line. All the way down to the center. So the very center echoes are going to be the shallowest or the least amount of phase encoding. So we're gonna have the lowest amplitude of phase encoding in our center echoes. And then we're gonna go in the opposite direction, right? So the echoes at the very bottom are going to have high amplitude, just the polarity is switched, right? These echoes are created with, they have a large amount of phase shift. How do we get a lot of phase shift? With a steep gradient, right? These echoes have little phase shift. And how do we get little phase shift? With shallow phase encoding gradients. Shallow gradient. And we fill them in a spin echo sequence sequentially. So echo 1, boom, 2, 3, 4, 5, 6, 7, 8, all the way down to the other side. In this case, I don't know how many there are, right? Like 10 or 12. The outer lines of K-space contain echoes with higher phase encoding amplitudes. So more phase encoding with higher gradient amplitudes. These echoes contain more information about spatial resolution. Write that down. The echoes on the outside of K-space are created with steep phase encoding gradients, giving a lot of phase shift, containing information about spatial resolution, but not a lot about the contrast. Remember I said earlier, every single echo contains information about the entire slice, right? The echoes that are heavily phase shifted with steep phase encoding gradients give us information about spatial resolution. This is an image reconstructed just using the outsides of K-space. I don't see the contrast there, right? But I see fine line detail. The middle lines of K-space have low amplitude phase encoding gradients, right? Like as we said before, little phase shifts with shallow gradients. These have lower spatial resolution, but have high contrast information. Here's that same image reconstructed just using the central portion of K-space. What do you notice? Can't see much detail, right? But I can see that it's a T1 weighted image. I see all my contrast there, right? In K-space, the center of K-space gives us information about image contrast. All outer areas of K-space give us information about detail and resolution. You can see now why it is stepped. Also, I don't know if you've noticed here in the other diagrams or in actual K-space, notice these echoes have higher amplitude in the center. This confuses everybody. The echo in the center is higher amplitude, meaning there's more signal. The signal amplitude is higher, right? But it was created with a low amplitude phase encoding gradient. We barely gave it any phase shift. That's why it has high amplitude signal, because it's more in phase than the rest of them, right? Remember, phase coherence gives us transverse magnetization, right? So when we do a heavy phase shift or a lot of phase encoding with a steep phase encoding gradient to provide detail information, this echo is not as in phase. It doesn't have as much phase coherence intentionally. Therefore, it has lower amplitude signal. Okay? If I phase shift my echo to make it out of phase intentionally, to give me detail information, it's not going to have as much transverse magnetization. And if it doesn't have as much transverse magnetization, the amplitude of that echo is going to be low. But it provides information about resolution. That's fine. It's good to have. On the other hand, the echoes in the center of K-space that had a low or shallow phase encoding gradient with barely any phase shift, they are more in phase, therefore they have more transverse magnetization. They give us most of the signal of the image comes from these echoes and all of the contrast information. So we do this over and over again. Each TR period, each slice is selectively excited. One phase encoding step is performed, one amplitude of the phase encoding gradient. All the frequency encoding points are sampled for that step of the phase encoding process. The more phase encoding steps that are performed, the higher the spatial resolution, right? The more phase encoding steps are performed, the more TR periods we have to go through, therefore longer scan times. The steeper the phase encoding gradient, the more dephasing is caused across the field of view, right? Intentionally. But because we do that to get resolution, we have less signal, right? So those echoes out here not only give us information about resolution, they also have low signal by the property of being dephased. Remember, we always talked about dephasing or loss of phase coherence as loss of transverse magnetization, thus loss of signal, right? Steep phase encoding gradients fill the outer lines of K-space. The outer lines of K-space contain lower amplitude signal and contribute to resolution details. There's another one right there with just the outer areas of K-space. The shallower phase encoding gradients, less dephasing across the field of view, therefore more signal, right? More signal. They contain higher amplitude signal. They contribute information about tissue contrast, and most of the SNR is there. Little edge resolution information, as we can see here. Fortunately, we reconstruct. This is why all of K-space has to be filled to generate the image. We need the outer lines and the inner lines, all of the aspects of K-space, to get a full image. Sequentially is how they are filled, like I said before, either from bottom to top or top to bottom. Right? High amplitude down to low amplitude, and then the opposite polarity back up to high amplitude. Next week, we will talk about how we can fill it. Center outward, we don't need to talk about that yet. That will be next week. But this is just showing us resolution. We've seen this before, right? Lower resolution.
To make an NMR picture and MRI as we know it.
We can watch this real quick. Does anyone else want me to explain any of this again? Or do you have any questions? I mean, I'm sure there's lots of questions, but is there anything that's like, you're 100% saying, nah, I can't get that, I can't buy that? All right. Yeah. Let's watch this real quick.
But today, we have to be able to localize the signals coming from the sampler.
This isn't perfect, but it gives you kind of an idea. When they start talking about isolating lines of phase, it's BS, but this is for those visual learners.
In 3D space. The first to propose a technique to do just that was Dr. Paul Latimer. In the March 1973 edition of Nature, Latimer published a brief article entitled Image Formation by Induced Local Interactions, Examples Employing Nuclear Magnetic Resonance. In the article, he describes a technique using magnetic gradients to identify the location of two 1 millimeter capillary tubes filled with water, both of which were submerged in a larger 4.2 millimeter tube filled with heavy water. Heavy water has the symbol D2O because the hydrogen atoms in heavy water are isotopes of the standard protium configuration with one proton in the nucleus. The deuterium atom, on the other hand, contains a neutron as well as the proton, which limits the spin of the nucleus and therefore does not give a good NMR signal. Latimer placed his apparatus in the high field NMR magnet as shown and developed a technique to identify the actual origin of the NMR signals from the standard water. This is the image produced, very primitive by today's standards, but clearly shows the location of the two capillary tubes of standard water. Latimer called his technique zeugmatography from the Greek zeugma, which means that which is used for joining. To show you how we make an actual MR picture, we're going to move our perspective of our spins from the side to the top and represent each grouping simply by the net magnetic field rotating around the axis. Remember that the Laue-Moore or resonant frequency of our spins is determined by the strength of the local magnetic field. When we first get into the MRI machine, a superconducting magnet creates a near homogeneous magnetic field from one side to the other that determines the strength of the MRI machine. Common systems are 1, 1.5, and 3 Tesla in strength. There are 3 sets of gradient magnets in the MRI used to localize locations in 3D space. The Z-axis, axis, then y-axis. To select a particular slice of tissue in the body, we can turn on the set of electromagnets along the z-axis that create a magnetic gradient from head to toe. We now put in a radio pulse with a frequency that will cause the desired area to resonate as described earlier. We have now selected our slice through the body. Because the local magnetic gradient is homogeneous, all of these net magnetic moments in the slice are in phase, spinning together in sync, and can't be distinguished from one another. To further localize these magnetic moments and their signal strength, we have 2 more gradients that we can use to isolate the source of the signals. The first gradient is called the phase encoding gradient. To demonstrate the effect, we're going to slow down our net magnetic moments. The phase encoding gradient is briefly turned on, creating a gradient along the y-axis in this particular case, resulting in the magnetic moments at the bottom of the gradient to slow down, and the ones at the top where the magnetic field is higher to speed up. The gradient is quickly turned off, and the spinning magnets return to the base frequency, spinning at the same rate, but they have now experienced a phase shift in the y-axis, which we can use to localize the spins in the y direction. We then tune our system to focus on a particular phase in the matrix and use our third gradient in the x direction to definitively localize each of these signals in the selected row. This gradient again causes the spins to the right to slow down and the ones on the left to speed up. This frequency encoding gradient remains on while the signals are recorded. Now, each of the signals has a unique phase and frequency which can be localized in 3D space. The whole process is repeated for each row, localizing, in this example, in the y direction with the phase encoding gradient and in the x direction with the frequency encoding gradient until the entire matrix is complete.
Hopefully that helped you visualize it a little bit better.
Yeah.
All right, I'll see you all next week unless there are any questions.
Yeah.